we have one session by research students telling us about their journey into research, systems research. Okay, so we'll begin with the first talk, which is by Dr. Devashree Tripathi, who is assistant professor in the computer science department at IIT Bhubaneswar. So Devashree did her PhD from University of California, Riverside, and then she worked at Harvard University for some time as a postdoctoral fellow, and then she joined IIT Bhubaneswar. So Devashree's main area of research is basically various aspects of computer architecture, including high performance computing, fault tolerance, and power efficient designs for accelerators and machine learning. So today she'll be telling us about heterogeneous systems. Over to you.
Thank you so much, sir. I'm really excited to be at the workshop on systems, specifically like looking at people who are interested to pursue their future in systems research, and or at least they want to know what is systems and is it going to be useful for them or not. So, okay, first things first. How many of you are aware about accelerators? Have you used any of the accelerators? Yes? Can I get some examples? What accelerators you have used? It's okay, no answer has to be right or wrong. Like, we are here for a discussion, right? Okay, DNN accelerators. Okay, anything else? Any other accelerators you might have used? How many of you like gaming? Or you are all studious folks, no gaming whatsoever, just studies. That's how you spend your time. You're into gaming? Do you use any GPUs? NVIDIA GPUs. Okay, so GPUs is an example of accelerators. So why are they special? Why do you need a GPU? Can you not manage with a CPU and like your game experience?
It's better to have some specific.
Okay, so from what I get, so GPUs are good with calculations, and you want to accelerate those calculations and have a better gamer experience. So that's why you go for GPUs. Is that right? Okay, all right, excellent. So without further delay, I'll proceed with the session. So yeah, the reason for asking you about accelerators or where I specialize in is especially GPUs, where I did most of my PhD work in, and SoCs, where I did most of my postdoc work in Harvard University, and it's still like ongoing work. So to be specific, in GPUs, I focused on the microarchitecture, compiler-assisted techniques, runtime for power and scheduling, and the thrust was primarily performance and energy efficiency. Like one of you said, like we want to have lots of calculations done at a very minimal time, right? We want a very less response time. That's what we call as performance. And second problem is the energy efficiency. So can you fit in n number of GPUs with your CPU and get a better experience? Is that a possibility? Like taking apart the cost, let's say you can afford n number of GPUs, and yeah, you can like get a better experience. Would you like to go for that choice? Probably. Yes, no, yes. Okay. So meaning it's a scalable setup. So you can fit in any number of GPUs and you will get a better experience. Okay. So as we proceed in the talk, we'll see if that thinking is in the right path or not. Okay. And the second thing is SoC, system on chip. So what is system on chip to you? Have you used any system on chip in your daily life? So the like low response or low energy level is because of a nice lunch hosted by IISc, or the topic is not coping up with your interest levels, or both? Okay, never mind. So system on chip is basically if you have a CPU as well as a lot of accelerators all residing on the same chip, then we call it as system on chip. Nowadays, we are using system on chip on many things, like starting from autonomous vehicles. So Tesla has a like specific system on chip. It's specified for a specific domain, like autonomous vehicles, or like your headset, like AR/VR headset, is also an example of domain-specific SoC. And the domain here in question is the AR/VR domain. Okay. So in the SoC area, I focused on the accelerator design, which overlaps with my PhD experience in the GPU area, and then hardware, software, code design. Let's say you have been given a set of application, like a code, C code, right? So out of that C code, some functions might be accelerator friendly, some functions might not be accelerator friendly. Let's say you have 10 different accelerators, accelerator A, B, C, D. So now the question is, when you are a programmer or a system designer, you have to answer this critical question, that is function A. Will it perform better if I port it or implement it on accelerator A, or will it be better if I port it on accelerator B or C? So you have a lot of choices, a set of accelerators given to you. Now the question that you're answering is like, where will this piece of code perform best? So that is answering those kind of questions is what we call as hardware, software, co-design. Next is machine learning for SoC design. Now ML has like entered every domain, like everyone wants to do ML. So we also have done some kind of ML used for SoC design, and then simulation methodology. So why simulation methodology? Let's say I want to design a system that has not existed before. So it's a new Tesla vehicle. Like the system has not existed before because I have some unique mind, like criteria in my mind that I want to test out with. So what is the best way to go? Should I like make a chip A, fabricate it, test it, or it does not work out, throw it away, and make another chip and test it out, and like this is how it should be, or do you have a better solution in mind? You go with simulation. So you have some pieces of code block mimicking the behavior of the hardware, and you tweak depending on your idea and see whether my performance or area number that is being specified by the like the client is matching with whatever I'm going with or not. So simulation methodology has to be streamlined to ensure that your ideas are working the way they should be. Yeah. And here, like the main focus was automated design space exploration. Let's say someone gave me a bunch of applications, said that, okay, Devashri, here you go. You have to give me a chip in, like design a chip for me in 2-3 months time. And it should fit into this much area because this is what I have dedicated for it. It should not exceed this much power. Why power is important, we'll see. And it should give me the best performance. So how am I going to meet these three functions, these three objective functions, which is performance, power, and area? And also at the same time, support all the functionalities that are defined by the set of applications that the client has given me and deliver the chip. So that's why the automated design space exploration is getting increasingly important. So now this slide basically tells why accelerators are needed. So in this trajectory, which is that in the x-axis, we have plotted the years, and on the y-axis, we have plotted the clock speed. So clock speed, the higher the speed, the better is the performance typically. So here we can see that we have hit a saturation point towards 2005 like area. So what do we do next? Like now my clock speed is not increasing, and this is the 45 years of processor trends. So what is my way out? But my computing demand, like I am like using the processors everywhere in smartphones, gaming, cloud data centers, and whatnot. So my computing demand is keeping on increasing. The number of data that is getting produced from the sensors that need to be computed and processed is increasing. But my hardware is not coping up with it, with the demand. So what is my way out? Any thoughts?
Instead of increasing the speed of one process, you could put two processes.
Exactly. So one processor is not helping, but can I like break my task into multiple subtasks and assign one processor per task? Means can I take use of some kind of parallelism? Yes, so yes. So parallelism is what which led us to think that okay, if CPUs are not helping with the cause, let's go towards the accelerators. So they help with the meeting the growing demand in the computation and give us more computational power. Some of the examples of accelerators are GPUs, general graphic processor units, FPGAs, field programmable gate arrays, and ASICs, application specific integrated circuits, right? So any example of ASICs that you know of or have used anywhere? So how many of you have heard about, yeah, sure.
Do motor drivers count like integrated circuits?
Motor drivers?
Yes, like those do they count as integrated circuits in basic or is that
So the drivers, if it's embedded in a chip, which has the brain of its own, has a processor of its own, then it will count as a ASIC. Yeah, it's not. So how many of you have heard about TPUs, tensor processing units by Google? Does it classify as a ASIC because it's specifically made to enhance the performance of machine learning and AI applications? It's specific to its domain. So yeah, TPU counts as an ASIC. So this is what a SoC contains. Like when you have like CPU as well as couple of accelerators all on the single chip, then we call it as system on chip SoC. And yeah, during my PhD, I focused extensively on the GPUs, and on the postdoc, I took a step back and looked at the holistic picture of how we can make things better, like to meet the design perspective of performance, power, and area. So in today's talk, I'll be spending most of my time on the GPUs, like how we can enhance the performance of the GPUs, how we can make the GPUs more energy efficient. I'll go through 2 or 3 areas, like mostly it will be motivational areas because I don't want to go too deep into what was the technique, exact technique I used, how does it compare with the previous work, because I'm sure you're all smart enough to dig deep into it once you're interested in it. So I'll basically motivate you on the different problems, what are the different research areas in this topic, and yeah, that's what the goal of this talk is. Next comes wherever there is an accelerator and CPU mentioned, one question that needs to be answered is latency versus throughput. So have you heard about the term latency in your BTech curriculum? Yes, what is latency? How do you define a latency?
time taken to something
Time taken for something to execute.
how instant it is going to take that action when you like something.
So when you're clicking on something, how much time will it take to execute? Okay. So can I, like, if I am putting a formal definition to it, let's say I have, this is my input, this is my output. My input is an application, output can be something, some classification results or something, depending on what I am looking at. So the time taken for the signal to start from the input and reach at the output, that duration, can I call it as latency? Yes. Okay. What is throughput?
How much input is been going at a particular period of time?
Okay. Yeah. So how much input is going at a particular period of time? So I have a nice example, analytical example to explain this. Let's say you are going from IISc Bangalore to the airport and you're going in a Ferrari. It will take maybe 45 minutes. So and like it can accommodate maybe 2 people at the same time. And like let's say you have many people and you are taking a bus from IISc Bangalore to the airport and it has let's say 100 seats. So here the throughput is 100, throughput is 2, but latency is 45. This one might be like 1 hour or 1.5 hours, right? So this is a classic example to explain the difference between a CPU, Ferrari, and an accelerator, a bus. So accelerators are good with producing high throughput because they can parallelize and process high amount of data at a given point of time. But CPUs are good with more serial data, and they at the architecture, microarchitecture of the CPUs are tweaked to give you very low latency response. As Professor Panda will be explaining in the next talks, how can you make the CPUs more faster and like reduce the latency even further. But the focus of my talk is more towards the throughput. That's what the accelerators specialize in. Yeah, so this is again like a, so the only takeaway from this slide that I expect is like different venues where you can publish in computer architecture are AS+, Micro, ISCA, TACO, and so on. And this is the brief overview of what my research focuses on. Primarily the thrust are the performance and the energy efficiency. So now focusing on the performance aspect first. And so let's say my GPUs, so first of all, I will go through the concept of thread block scheduler. So how many of you have heard about thread block scheduler in the context of GPUs? Okay, so let's cover up some basics and then we'll go into the problem definition. So my application is broken down into multiple kernels. Let's say machine learning application. It has like a pooling layer, convolution layer, again pooling, convolution, and so on. So each layer you can visualize as a kernel. Kernel is defined as a bunch of functions. So, and here each kernel is dependent on each other, which means kernel 1 has to finish execution first, then kernel 2 can be launched, and then kernel 3 can be launched, and so on. So this is how we are visualizing a kernel. So this tilted lines are threads. And I'm assuming in the computer architecture course and the OS course, you're well versed with what the threads are and how they process the data and all those things. So I'll skip those portions. So this block are called as thread blocks. Here the data, we are dividing into a couple, like inside a kernel, we are dividing the data into some blocks of data called as thread blocks. And then the thread block scheduler has to map those blocks of data called thread blocks to the hardware, where like the hardware is called as streaming multiprocessors. It's same as your course, it's just that it has multiple of cores because you need to parallelize the data, right? So you have multiple of cores, and this is what the thread block scheduler does. Take the data in form of thread blocks and map it to the streaming multiprocessors or multiple cores. So now, talking about the first work, which was published in Micro 2017, we tackled the problem that the GPUs were not efficient with the data-dependent workloads. So what does data-dependent workload mean? Means the dots which are numbered are basically different kernels. And like we saw that kernel 1 was the parent kernel, it has to be finished first in order to execute the kernel 2 and so on. So this is the dependency graph, let's say. This is common dependency graph that we see in many graph applications, wavefront applications, and so on. So at the TP0, or like this is the TP0 has to finish before, so that TP1 and 4 can be executed and so on. So previously there was a problem with global barriers. What is global barriers? So here the blue portions that are highlighted are basically each kernel. So first kernel had only one thread block, second kernel had two thread blocks, third kernel has three thread blocks, and so on, right? So if I want to launch my second kernel, I have to finish my first kernel. And if I want to launch my third kernel, I have to finish my second kernel. But here, like the dependencies, if you can see, take a look at thread block 8, like its dependency is satisfied as long as the thread block 4 has finished executing. But still, because you have this global barrier synchronization primitive in place, you cannot launch the third kernel, which comprises of thread block 8, 5, and 2. Because of that, it's not possible. So that's what our research focused on, that how do you make it possible? Because what are the problems that are happening here? So here, like this thread block is sitting idle, though its dependency has been satisfied. So if a thread block is not getting scheduled, which means the corresponding hardware or the SM is underutilized. And underutilized comes at a cost of high static power, because if some resources are sitting idle and you're not utilizing them, you are like indirectly increasing the execution time, or the performance reduces, right? So this is an example of the Fermi GPU, which was like the very initial grade GPUs. So first, the CPU will launch the kernel on the GPU, that was my kernel 1, and once it finished executing it, the control will go back to the CPU, there is some synchronization happening at the CPU side, and then it will launch the second kernel and so on. So this was the flow that was being like done in this for these GPUs. So there was a high CPU side kernel launch overhead after every global barrier, because the communication each time you go from the CPU to GPU and GPU to CPU vice versa, it takes some amount of communication overhead, which like taken cumulatively becomes a huge overhead in the overall execution time. So then NVIDIA came up with something called CUDA dynamic parallelism. So you don't have to go to the CPU every time you finish up a kernel, but like let's say this thread has finished, so it can spawn another bunch of thread blocks and so on. So you're in the problem of global barrier synchronization or the CPU side, enforcing the synchronization to happen at the CPU side is no longer a requirement. So you have like mitigated the issue, but still, let's say in my previous graph, I had multiple parents having single child. Here, that case is not possible because only one to many forks are possible. The reverse is not possible. So the multi-parent dependency is not supported in the CUDA dynamic parallelism. So the work that we did is we provided a more generalized support for the fine-grained interblock data dependency, where the block is basically a thread block that I'm referring to. So inside a thread block, how can I maintain the dependency? If there are multiple thread blocks that are synchronizing with each other, like a complete graph, how you take care of the dependency and so on. So to sum up the motivational effort, so the current limitations were the high device-side kernel launch overhead, and there was no generalized support for interblock data dependency. So the paper, we call it as wireframe, has this hybrid hardware to software solution where we like launch specific thread blocks into a specific hardware or an SM, and it helps with meeting with the parallelism, dependent parallelism thread block scheduling, and the main focus is meeting the interblock dependencies. So yeah, now any questions on the wireframe? Because I have not gone through the solution as such, just a motivation of what are the different flavors of research done in the GPU microarchitecture area, focusing on performance enhancement. Yes, sir.
How do you know the dependencies? Is that given up?
So there are two ways. One is if the programmer or the application, the person who's writing the code is well aware of these are the kind of dependencies, then that's one way. Second is from the compiler analysis, we can extract what are the different dependencies, and then we can form that graph that I showed and pass it on to the hardware. Interesting question. Thanks for asking. Okay, so if we don't have any questions, we'll proceed into the next topic for performance enhancement. Caches. How many of you have heard about caches? All right, excellent. Yeah. So why do you use caches? To reduce the time that it needs to access the memory. Okay. So are there any drawbacks of using caches? Or no, there are only good things about caches? Okay. So is it a possibility that things that you're getting into the cache, but you're not reusing it, you are again throwing it out and again getting a new data? So is it a problem with caches or no? You don't have to worry about it. Sorry?
You have to worry about the hit rate.
You will have to worry about the hit rate. So caches are important or useful only when you have much locality in your data or you're looking for reusing the data again and again. But if it's a streaming application, so you're just bringing the data in, using it once, and then moving ahead and bringing the new data in, and then like processing it. So it's not going to be useful in that case, right? So you have to make sure that if you're using caches, you have to increase the cache reuse. You have at least, or like the application has to be programmed in such a way that it has high cache locality. So that's what the next problem that we have is being we are targeting on. So GPU have a very small cache per thread. So if I ask you a quick question, so what is a typical L1 cache size in a CPU? we need to search something on Google, right, to look at what are the typical cache size in CPUs. Okay, so it's significantly high than the cache size in a GPU. And second thing, in a CPU, we can launch a specific amount of threads. We have a limited thread that we can launch. But here you're launching like maybe thousands of threads, which means each thread are using or accessing the cache. And there has to be some kind of synchronization, or else each thread will keep throwing out each other's data out of the cache. And the performance will now suffer, right? So if I have smaller caches per thread, then the immediate solution will go to our mind is, what's the problem with that? I don't see a problem. Let's make bigger caches like we have in CPUs. What's the problem with having bigger caches? Area and power of the bigger caches will be more. What else? So cost as in what cost? Performance cost. Okay. Yes. And also the access time will increase, right? So let's say you have a bigger room. To find an object from a bigger room, you'll need more time than finding an object from a smaller room. So same applies for the caches. The access time will also increase. So some of the papers that in Micro 2012, they have validated the fact that going forward, due to which we are ineffective in hiding the memory access latency. So, and which also leads to memory subsystem congestion. Can we increase the cache reuse? Can we do some magic either in the code or in the microarchitecture or somewhere in the middle to increase the cache reuse? So before we can answer or put our thoughts in that, so I thought a little bit of focus on what is the cache scenario happening in the GPUs from a thread block scheduler's perspective is important for us to know. So this is the default thread block scheduler. On the top, I have this GPU workload. Workload can be anything. Let's say particle simulation, where like the dots are different particles, and like I have divided the workload into different thread blocks. For the simplicity purpose, I have used 4 thread blocks. But in the real GPUs, there can be many thread blocks. In this example, I have used 100 thread blocks in that workload. So that is what my software will map. And then comes my GPU hardware. So in the middle of GPU hardware and the software, there is a thread block scheduler, which we saw in the previous slides. So within a GPU hardware, we have some streaming multiprocessors, SMs. You also have a L2 cache, L1 cache, and then we have a shared memory, and we have multiple of cores, and then we have a DRAM or a memory, right? So this is how a typical GPU memory hierarchy looks like. So now the question is, if I want to increase the cache reuse, or let's say if I'm not doing a better cache reuse, what will happen? Everything will overflow from here. And every time there is a cache miss from here, you will have to access the L2 through interconnection network. And if there is a miss here, you will go to DRAM. So there is a huge memory congestion because thousands and thousands of threads are running. So if every one of them sends the request to the memory every now and then the network on chip will be, there will be a huge memory contention, and it will show up in your performance results, right? So here the way the allocation is done, let's say how many thread blocks can be accommodated at a given point of time on a SM. So what are the major factors or the players that matter in this case? First is how much shared memory I have, because every thread, the way we code is, right? Every thread uses some portion of the register, they use some portion of the shared memory and so on. So depending on how much hardware limitation I have, my shared memory size, register file size, and maximum threads per SM, I decide, okay, maybe 3 thread blocks can run at a given point of time in an SM. And why am I explaining all this? Why is it important how many thread blocks can run parallelly on an SM? Any thoughts? Why are we spending time on discussing this specific detail? Yeah, so if there are multiple thread blocks running on an SM, then like they have to be in sync with each other so that we are using the L1 cache more often, right? So which means less misses generated from the L1 cache. So now what happens, like from the previous slide, for the assumption we have taken maximum thread block that can run on an SM is 3. So here in this illustration, So TB0 goes to first SM, TB1 goes to second SM, and in a round robin fashion, that's what the default thread block scheduler is. This is how we are distributing the data. Then what's the problem with it? The problem is there is some data that is shared across the boundary of TB0 and TB1 and so on. So are we taking into account those common data sharing among the thread blocks in the default round robin case? No, right? Because TB0 and TB1 are going to the two different SMs, which means there will be some L1, like less reuse in the L1 for both the SMs. So next, the question that we try answering is, okay, we saw an example where there was some data sharing between multiple thread blocks in the boundary cases. But is it common or it is specific to one application? If it's specific to only one application, we don't have to worry about it. But if it's a common pattern that we are seeing in multiple applications, then we need to think seriously about it. And maybe we can design a scheduler to account for such kind of thread block locality. So to study this further, to answer the first question, how common is this data locality? We basically took a bunch of applications from some benchmark suits, and like on the y-axis we have plotted the data reference distribution. So and the one which are boxed by red lines basically show how much inter TB locality that we have, so that people like the thread blocks with high locality can be pushed to the same SM, so that we can get maximum L1 cache use. So, and then we saw that like there are three primary patterns that exist in the TB locality. One is the row-wise TB locality, which is seen in the matrix multiplication application matrix A, where the form we define in the CUDA code is rho multiplied by n, where this row value for all the thread blocks belonging to the same row will be the same, showing high locality. And similarly, the second pattern is the column-wise locality, which we saw like exist among the columns of the thread block, again in the matrix multiplications, or it can be completely arbitrary, which is commonly seen in the graph applications like DFS, sparse matrix vector multiplication, and so on. So for the first, like the row-wise or column-wise, do you think can we think of a solution how to mitigate this, or like how the thread block scheduler should be? Any thoughts? So, yeah, we can have a sliding window, or if we can see that okay, this is the pattern that exists, we know that like the thread block map, like the same row or same column can go to the same SM. We'll try to maintain that as much as possible, right? But if like this is basically algorithm dependent, but if we have something which is completely arbitrary, no algorithm can define the pattern, then what do we do?
Can we try applying convolution?
Sorry?
Can we try like convolving that matrix to a representation where it's going to be either row-wise or column-wise?
So you can definitely modify the application, but here, let's say you have a graph application and your input is dependent on what is your input graph, right? So even if you have written an algorithm, but you are unaware of the input graph, so you cannot change the behavior to represent a specified pattern. So yeah, basically we looked at the different prior works which might have or might not have looked at all the locality patterns. And what we saw was that the prior works were focusing either on this pattern, which is commonly known, or this pattern, which is algorithmically defined. But they have missed out on the arbitrary pattern. So to answer it, first we looked at the source code. We identify the locality information from the source code, and then come up with a graph where the node ID represents the thread block ID and the edge weight represents how many common data items are being shared by different thread blocks. And then we can go with a graph partitioning technique so that we can assign each piece G1 to SM0, G2 to SM1, and so on. So because it's a graph partitioning technique and it's a very generalized approach, so once you can identify the locality information and come up with that locality graph, your problem is solved. You can map those thread blocks having more data sharing to the same SM so that we can take advantage of L1 locality, L2 locality, and also the memory. So that was our paper which was published in TACO 2021, the second one. So these two papers primarily exploit the different thread block scheduling techniques to increase the performance benefits. Then I thought, okay, performance is great, but there was, because of the Bitcoin mining, there was a, like we're looking at the climate changes that is happening, there is a lot of power that is the GPU is consuming and so on. Then I got curious and I looked at the power effects. So with the different generation of the GPUs, and this the years is like what year they were launched, we saw that the performance is increasing, but at the same time, the TDP or thermal detecting power is also increasing at the same rate. And what happens if the power increases? Is that a problem? Do I have to worry about it? Like more power means more like heavy, fat electricity bills. Apart from that, anything else that we have to take care of or not? Heat, yes. So if you have more power, and because the circuits are placed close to each other, they will have a heating effect, and they might ruin each other's behavior because of the inductive heat effect. So with the power, with the performance demand, the power is also increasing, which means if we keep increasing at this rate, then we will hit a power wall problem. This is what the power wall problem is, which means we will soon reach the temperature of a nuclear reactor, which means it's not a sustainable solution, and it will have reliability issues, not very, like it's an expensive solution and not environment friendly. So now, because I had spent some time on microarchitecture, then we looked at like what are the different microarchitecture improvements that can be done to increase the performance demand without increasing the power consumption. So I know my application behavior. Can I do something fancy or some modifications in my microarchitecture to make sure that the power does not increase, but the performance still increases? So for that, we looked at like what is the most energy hungry component on the chip from the storage point of view. So we did a like comparison of the L2 cache and the register file, because we have a lot of threads in our GPUs, and each thread has a dedicated register associated with it. So the register file for the whole GPU is way more than the L2 cache. This pattern is not seen in the CPU, it's specific to the GPU. So then we turned our focus on the register files, that okay, they are if the size of the storage structure increases, then the static power associated with that also increases accordingly, right? So next, okay, so for us to see if we can save some power, some static power in the register file, we have to see how often are we increasing it. Is there a way we can switch off the registers for some certain amount of time and save some power and so that. So to see what are the patterns that the register files have been used in, we did some analysis. And this is what we got. For different applications, if we like put the cycles per count, so these are the ideal cycles that basically this shows the register file underutilization, and these numbers basically show the amount of ideal cycles between two consecutive access to the same register, which means like majority of the portions the register is being idle. So if it's idle, does it make sense for me to switch off it or put it in some low energy consumption mode, and then we can save some static energy? So that's what the direction we thought in. So, and then little bit of like, can I randomly switch off anything, or there are some considerations that I have to take before putting the registers to sleep and so on. So before putting the registers to sleep, or what is my best break-even time, what should be the minimum idle period so that I can put my register to sleep? So there were some analysis involved. So this is a very quick pick of what we did. So on the y-axis is the voltage. VDD is the maximum voltage that the system runs on. So this thing applies for the transistors as well, right? So, and here, like for switching off any circuit, so the capacitors involved is the RC circuit, right? So the capacitor has to discharge completely for the voltage to become zero, And then when you want to switch it on, it has to like charge completely. So there is some time, delay time. It's not that, okay, at time 0, I switch it off and immediately it gets switched off. All the charges, all the voltage drops down to 0. It's not the case, because depending on the circuit, the size of the capacitance and so on, it will take its own sweet time to discharge and recharge again. And if I distribute it, then basically we call it as idle detect, sleep delay, fall time, and rise time. And this is my total break-even time. Let's say I have to put something to sleep. My idle period has to be more than this TBD or break-even time to get me some positive energy gains, or else I'll be spending time and energy to switch it off and switch it on again without saving some time. So this period has to be also something long enough, right? Like the idle period. So what if my idle period is less than the break-even time? Am I going for negative energy saving by like incorporating all this technique? Am I losing more energy? So then we thought that okay, even if we cannot switch it off completely, if we can put it under some low power mode, VDD dash, which is less than this VDD, we can still save some energy, right? Because static energy is proportional to the voltage that we have. So which is also called as drowsy voltage. So drowsy voltage is the voltage at which you are still retaining the data in the registers, but you are not consuming as high power that you would have in the VDD. So similarly, and if you choose something intermediate, again you will have to like a trade-off between how much you are saving and how much static power it's consuming. So the undervolting, the takeaway from this slide was undervolting had shorter transition times, and the break-even time can be reduced considerably at the expense of little more energy. So after that, we did a analysis of how much should be the idle period and what should be the voltage correlation and how much will be the power saved in this case. And then we reach at a sweet spot, which is meeting our objective of saving the power of the register files in the GPU. And the minimum retentive voltage was set as something close to 0.3 voltage. So retention voltage is the voltage where we will not lose the data. So here, there were another two important observations. If you are writing into the register, there is no point for you to retain the data because anyway, all the contents of the register are going to be overwritten. So you can just switch it off and put it at 0 voltage. But if you are reading from the data, then it makes more sense to put it at minimum retention voltage where the contents are safe and you're not losing the data and still saving some energy. So I'll skip this slide in the interest of time. And then focusing on the state. So this was all because we are tweaking the microarchitecture. We had to take help of the simulators and like get some analysis results on how the combination of power gating and undervolting can be used to save the static energy in the register files. But then the next question comes, is it possible to do something like this in the real GPU? So definitely not specifically for the register files because you cannot hack the register file in a real GPU as is without any specific APIs and so. But we tried to undervolt the whole real GPU and see its effect on the energy efficiency and reliability. And so the goal here was I'll undervolt it fine, but which will means that like I'm reducing the power, but it might increase my execution time. And overall, the objective is to increase the energy. But does it have any problems like will it have any faults because it's a real GPU, right? So it might have some faults because if a manufacturer has specified a specific voltage range, which means if you are not sticking to that specific voltage, also called as V minimum, then you might incur some errors. So if you are incurring some errors, then we are basically trying to rectify those errors or those faults at the runtime and still save some energy. That's the primary idea that we had here. So yeah, and after that, we played around with overclocking plus undervolting. If I overclock it so that my application finishes soon, which means I'm saving some static energy, in combination with undervolting in the real GPU, am I saving some time and energy in that case? So this is all like the time and effort on the GPU performance as well as energy efficiency spent. And I'll end the session with a very quick peek of what is the SOC research that we are focusing on and why it is important. So first of all, the SOC, why is it needed? Because as we can see, the GPUs or any general purpose devices cannot give you the peak maximum performance because they have these components that can, let's say a GPU will have a like matrix sign unit or a special function unit or a division unit and so on, but your application does not use those special function units. Like for example, matrix multiplication, it's a bunch of the ML application is a bunch of addition and matrix multiplication, right? So you don't have to spend or like the chip space designing any special function units. So you can use that space to like put more of the units or the functional components that are going to help you increase the performance. So the DSOCs are important because general purpose processors, example CPUs and GPUs, are flexible and programmable, but they're not as energy efficient or as fast performing as the ASICs are. So ASICs are more specialized in terms of performance and efficiency. So DSOCs are getting the sweet spots of both of them, ASICs as well as the general purpose processors. So to bridge the gap between the increasing compute and data requirements, as well as diminish the benefits from the technology scaling, the efficiency gap, the DSOCs are now like a major focus currently. So the brief overview of DSOC research is, let's say you have an input application, let's say 10 reference application has been specified to you by the client. Let's say autonomous vehicles is the domain I'm talking about. From the compiler, you will draw like what are the application characteristics, what are the areas where I can parallelize it, what are the serial areas, how does my application looks like, and so on. And then I can do some design space exploration to come up with a finalized microarchitecture, implement it, and then the chip tape-out comes into picture. So my focus is on the part where it's highlighted in red, where like a simple CPU, right? So if I want to design a simple CPU specified for a specific application, I can have so many different configurations of the register file. I can have so many configurations of the caches. I can have so many configurations of the memory. So this basically becomes a huge design space. How do I like generalize it and come up with one specific design point that will meet all my performance and power criteria? So that's what I am spending most of my time and effort on, and how I can use the ML, especially for coming up and answering these questions that we have, and maybe possibly extend it to different multiple SOCs where the two SOCs sitting at different locations can talk to each other, and basically we can come up with a better microarchitecture for it. So yeah, this is pretty much it that from the accelerator design point of view and the SOC design point of view that we have spent time on, and I'm happy to take any questions that you might have.
Any questions?
Yes.
Yeah, yeah. Go ahead. Can you hear him? Just speak it louder than you want in the mic.
When you talk about synergistic DSC, it is like you start at a small set of microarchitectural parameters and start expanding for the become
So yeah, it can be both, right? Like currently, let's say for the simplistic purpose, I'm not tweaking the internal details of a CPU or any accelerator. I'm taking them as is and seeing how many of them I can map into my processor. But yeah, the next step is like, let's say this specific component, let's say this amount of register file is helping improve my performance. I'll basically make clones of it and I'll have more of it. So yeah, it's basically back and forth process. This is what we are calling as synergistic DSC. So yeah, you are right in this way, but like for the simplicity purpose, we can also start with just without tweaking one IP block. let's say CPU or GPU. Thanks for the question.
Any other questions? Yeah, Prabhu.
So when you say cache reuse, how are you measuring? You won't know whether you are hitting on the same cache line or distributed across the lines.
So yeah, so the cache use basically the way when we profile the data, we are looking at like what are the memory address it's going into, rather than looking at what exact cache line it was mapped into. We are looking at exact data location.
Yeah, but how do you measure the reuse?
So yeah, basically from the when we are getting with the application, right? So we are profiling it and looking at like, okay, this data item is pointing to this specific memory location. And then we are finding a set of how, like this thread block, what are the different memory locations or the data locations it's touching on. And another thread block, what are the different data items it's touching on. And the intersection of that set is what we're defining as cache reuse or the data items reuse. Did I answer your question? Okay.
Just a trivial query. So in GPUs, your cache hierarchy is exclusive or semi-exclusive? What exactly it is?
So the cache hierarchy is inclusive actually.
In GPUs too?
Yes.
Why? What?
So because like the cache consistency and all is not well defined as of now. So the cache coherence protocols and all that is not that implemented as of now.
Good to know that.
So another potential area of research.
Also, in your, I think the scheduling for those thread blocks. So in one situation, you said you'll find what is the kind of commonly accessed data. How easy is that to figure out statically from the program?
So statically, if it's application dependent or the input is known a priori, it's easy from the profiling or from the compiler static analysis, we can do it. But if it's not known, then like we have to do some extensive profiling.
Just profile and find out which
yes.
one. Okay, so if there are no more questions, let's thank Devashri. And on behalf of the organizers, I'd just like to hand over a small memento. Thank you. Thank you. So our next speaker is Dr. Biswa Panda, fondly called Biswa for short. So Biswa is well known for his work in high performance cache compressors and multi-level hardware data prefetchers. So I think these are like the state of the art systems. And he's a recipient of several awards, including the Qualcomm Faculty Award, Google India Research Award, and the Kriti Ramangaram Award for Creative Research at IT Bombay. Today, Vishnu will be telling us about pushing the limits of hardware prefetchers. Please welcome.
Can you hear me? Last row. Okay. So before we start the talk, how many of you are feeling sleepy? Including me. Only two. We'll give special lunch if you say you're feeling sleepy. Okay, I hope this talk will be a fight between your sleep and prefetcher. Okay. So I hope it works. Yeah, so for the next 45 minutes or 1 hour, I'll just talk about one thing, one keyword, which is called prefetcher. We'll see why it is important and why we should care, right, in this workshop. Before that, since there was a lunch break, make sure your smartphones, or even if you have non-smartphones, it's on silence. Okay, thank you. So, how many of you are aware of these terms? Latency, bandwidth, they obviously talked about it. So my job is easy. Bottleneck. What is bottleneck? What is it? You can say make up the bottleneck. No? What like why are you discussing about bottleneck? What's the utility in computing system? Sorry? Why? Because slowest part of the system. Any other answer?
Congestion. Congestion.
Congestion? Anything else?
They limit the rate.
It limits the rate. Okay. So no matter how fast your whatever system that you are designed, if there is a bottleneck somewhere, right, that will limit your overall throughput or performance or whatever. Cycles is nothing but latency. Again, AMD folks talked about it. Devasi talked about it. Sarni talked about it, right? CAS. I think all of you are expert. Anyone who is not an expert on CAS? All of you are. Cool. DRAM. I'm not asking the expansion of this acronym. Any relationship between these two? What is it? Go on, like feel free to answer anything.
Cache is also a type of memory, but it's different from DRAM.
Yeah, the name is different, so it has to be different.
The function is also different.
Sorry?
The function is different. Cache exists so that you don't have to go to DRAM.
Okay. So sorry. Runtime allocation. I don't think I'm able to connect it. But cache is kind of helper to DRAM. I think I kind of agree with them. And finally, processor, CPU, core. Everyone understand that? Instructions. What is an instruction? Come on, it's a recursive definition, right? Instruction is set of instructions. Come on. Yeah, exactly, right? So this is a language of processor. The language doesn't understand your Python, C, C++, right? So this is a language of processor. Okay, so fair enough. So I work in the field of microarchitecture. 10,000 feet view about microarchitecture is, this is your famous chip that is there on your mobile phone or laptop or desktop. So you will find there are many hardware algorithms which are there inside this chip, which are not exposed to programmer. They do all kinds of magic to make sure you get your performance, energy efficiency, security, and blah, 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 right? So I work in these topics, and my primary goal is, this side of the performance rating. Okay, is that fair enough? Is this clear? Okay. So in the context of workshop, anyway, this is the last but one talk, right? So you should know where am I, right? I'm here, right at the bottom. And this is actually the enabler for everything else that you guys discussed from last 3 days. Because this guy actually takes care of almost everything. Okay? So, but finally the question is it relevant? People have been talking about GPUs, accelerators, quantum processors, and whatnot. Right? So it seems like I'm an old school guy. Okay. So how many of you have heard about this guy called Alan Kay? Okay, just one. Cool. Yeah, expected. So I just go to this particular statement, which is slowly becoming true in the modern computing world. So you will see that software companies are now designing their own hardware, their own CPUs. Okay, and when I say software companies, they are all the big ones, right? So whatever you have heard about, like your Facebook, Amazon, Microsoft, Google, even Nvidia, which is supposed to be a GPU company, Nvidia is designing its own CPU. Okay, that means whatever I'm talking now or what I'll be talking for the next 45 minutes, it's relevant. Okay, so don't sleep. So time for the talk now. What I will do is I will talk about few techniques which are related to hardware prefetching. We'll understand what is it, and we'll try to see how we can improve it one step at a time. So that's the title of the talk. Okay. So the context of the talk, we are running programs in CPU. Okay. So you can assume any of your favorite chip. It can be from Apple, it can be from Intel or AMD, right? And let's take a simple application that all of us use in day-to-day life, which is called web search, right? So what we'll do, we will run this application in one of the latest Intel processor, and then we'll try to find out the bottlenecks. Okay? If you're still feeling sleepy, bottleneck is something similar to Bangalore traffic. Okay? So we'll try to see what limits the performance of web search when you run it on your Intel as well. Okay? So microarchitecture, if you look at it at a high level, it's a game of latency and bandwidth. So this guy demands data and instruction from memory, and this guy delivers at a fixed rate, and it has its own limitations in terms of bandwidth. So bandwidth is nothing but throughput, whatever Devasri talked about, right? So if you send a request, you get it after T. So that is actually your latency in terms of T cycles, and bandwidth is in one go up to what extent you are pumping your data or how fast you are pumping your data back into the processor. Okay. So keep in mind the application, web search. So like web search is running here, this guy is demanding for data and code, and we are interested in the bottlenecks. Okay. So since these two guys are actually far apart, because you won't find the DRAM inside your chip, DRAM is actually outside of your chip, so it's actually long distance relationship. Okay, so it will take hundreds of cycles just to get few bytes of data, right? So what you do, you bring multiple levels of cache, and their job is to hide this latency, this North Pole, South Pole distance, right? And if you have a small cache closer to processor, it gives data pretty fast, one cycle, and there are some which are a bit fat, they will take tens of cycles, okay? But if you look at your program, this is the web search, which is running in your CPU, that can actually demand GBs of data. But we are talking about MBs maximum. Okay, so definitely you will reach DRAM. Not frequently, but still you will reach it. Okay, so our goal should be to make sure all our data resides here by some magic. Okay, so is this clear? What's the utility of a multi-level cache hierarchy? Okay, so now coming back to the application, which is pretty famous, we'll try to analyze where exactly this bottleneck is coming from. Okay, so if you look at this pie chart, for this talk, I'll be focusing on this two bottleneck. One is called backend memory, another is called retiring bottleneck. And if I add this two, this contributes to more than 50% of the bottleneck when you run your web search application. Okay, so let's try to understand this one first. Then we'll go for this one, and then we'll try to solve it. Okay. So backend memory bottleneck is nothing but the bottleneck or the latency that this guy has to pay for when it demands the data. Okay, so your modern systems will have an instruction cache that stores the code, the binary, which is mostly in few kilobytes, unless you are running it in a data center with MBs of footprint. So you'll find your L1I is actually giving you a pretty high hit rate. That is for the code. But for the data, it has to wait for either L1D or L2 or DRAM, depending on whether the data is present in one of these labels or in DRAM, right? So for that amount of time, this guy has to wait. There is no other way. Okay. The other bottleneck that I talked about is called retiring bottleneck. And here, I'll take at least a minute to explain this. So modern processors, what they do, they actually fetch multiple instructions in one cycle. Okay, so in one clock cycle, your processor can say, oh, okay, I can actually fetch 5 instructions and make them ready to get executed. So in this case, these are the 5 instructions. But then the moment it comes to the stage of execution, they are in a completely, they are getting executed in a completely out of order way. Okay, so which means even if this instruction is instruction number 5, as per the order given by the programmer or the compiler, this guy may finish fast, this might, or maybe this instruction 3 can finish fast before other instructions are done. Completely out of order, provided they are independent. There is no dependency. Okay. The catch here is to make sure we provide a program order or a precise state to the programmer. We need to retire these instructions in the same order in which they enter. Okay, which means even if this instruction 2, 3, 4, 5, they are done in let's say 30 or 35 cycles, they have to wait for this guy to finish. Okay, and in this case, this guy is actually getting a miss at all the levels of cache, going to DRAM. It's taking 300 cycles. So it means all these four instructions will be retiring from the processor after this 300 cycles. Is this two bottleneck clear? Retiring and backend? Okay. So if you look at it, even if you have L1 hit, right, which is taking 5 cycles, because of this retiring bottleneck, it may become 300. Because it has to wait for the first instruction to finish. Okay. Now, what should be the dream to solve this problem? L1 cache. Right? So that's what I have written here. So if you come up with a cache that gives you 100% hit rate, then problem solved. No need to go to L2, L3, forget about DRAM. Right? So then all your memory access latency will be just 5 cycles. That's the access latency of your L1D cache. And the long distance relationship that we have been talking about, it's over. Right? Okay. But that's a dream. So let's back to this workshop. But this will be the effect of the dream if this dream becomes true. What will happen? All the memory instructions will take 5 cycles. So even if there is a retiring bottleneck, it will just for 5 cycles. You know, instructions won't be hogging particularly few instructions at the retiring stage. Okay. So now the problem is clear. So we need to understand how to solve this problem. Okay. So that's where micro architects come, and their job is summarized here on the right hand side of the slides. Okay. So what you do, you come up with an idea. If it doesn't work, good, right? But if it works, then okay, I think that answers, right? Yeah. So that's what I do. Okay. So most of the time things don't work, and one fine day, you know, if something works, you need to seriously dig deep, finding out why exactly it's working. And that's what the computer systems research is all about. Okay. Apart from coding, debugging, and all the other things. Cool. So the magic that I've been talking about is in the form of a microarchitecture unit called hardware prefetcher. Okay. So this guy actually sits beside a cache, and it looks at all the requests that is coming to cache. Okay. And based on the past accesses, it does all kinds of magic and say, okay, if these are the past accesses, then this should be the future access. It goes to memory before time, get the data for this address, into cache, so that in future, when the processor actually demands for the data in this address, it will get a hit. That's why the name itself is pre. Right? You're fetching something before time, right? All good. So what we need now, we need a prefetcher that can provide L1 data 100%. If we can achieve that, then we are done. Yeah, question.
So the prefetcher sits
Yes.
So when I take like prefetches, does it fetch directly from the core or sorry, from the memory or from the L2 or L3?
Wherever it finds the data.
So it checks on.
Yes. There's only one way. Okay, you have to go through L2, L3, and then DRAM, and coming back again through L3 and L2. Okay. You can do some fancy optimizations to bypass, but the typical path is the one-way path. Okay. So now let's understand what are the trade-offs, right? If you want to design a prefetcher of L1, it should be lightweight. Your L1 cache size is few tens of kbs, like 32 kb per se. Okay. It should be highly accurate. Then only whatever you are speculating that, okay, these are the future memory accesses, they will get cache hits. Okay. High coverage, can anyone guess what does it mean? Prefetcher should deliver high coverage. Sorry?
Work across different applications.
That's here. It should work across all kinds of application and access patterns. So accuracy is all about how accurately are you predicting the future memory access. Coverage is what fraction of cache misses you are converting into hits. That's the coverage. Okay. Ideally, you need 100% accuracy. and 100% coverage. Then you will realize your dream. Okay. So a bit of history. This is not a new field at all. Okay. The first prefetcher that came, it was around sometime in the 90s, 1990s. That is there in almost all the mobile phones and laptops that you have been using. But mostly from last few decades, research was happening at the L2 prefetcher level. Well, L2 provides a sweet spot in terms of all the trade-offs that we discussed, and you can actually get a better playground if you want to play at the L2. Okay, but our dream is to provide L1 hit rate of 100%. So if I design L2 prefetcher, it won't help me. So L2 prefetcher will hide L2 to DRAM latency, right? But L1 to L2 is still there, right? So can we outperform all the prefetchers that people have proposed at L2, but for free, because it should be extremely lightweight, no complexity involved, and finally it should have higher accuracy and coverage. Okay? So that's what we did. I won't talk about this work in detail. I have been talking about it for the last 4 years. I should stop now. Okay? So these are different prefetchers which are actually at the L2 level. You can look at their size, tens of kbs, hundreds of kbs. And this is the performance that you get out of this prefetcher in terms of a single thread running a single CPU. Okay, higher the better. So this is our proposal. It's not even a kilobyte. It's like few hundreds of bytes, but it beats the state of the art by 2%. We'll see whether this 2% matters or not. That's a different discussion. But the idea at the high level was, instead of proposing a pretty highly complicated prefetcher, we decided we'll have a bouquet of tiny prefetchers, which are extremely tuned for all kinds of memory access patterns. Okay, so they work as a team instead of an individual prefetcher. Okay? Yeah.
Where does this prefetching code reside?
So this is a microarchitecture, as I talked about, right? So this is a structure. This is nothing but a small cache that just probes all these accesses and then try to speculate what will be the future. So this is sitting just beside your cache. Okay, but the proposal that I'm talking about, it will take only 800 bytes. This guy is 48 KB. Right, order of magnitude difference.
So these have to be, they have to be fabricated, or?
Yeah. This is the same thing. So initially you start doing architecture simulations, and then once industry finds merit, they will actually put it on. Huh.
The entire bouquet is 800 bytes?
Yes. Yeah.
Percentage, 45%, 43% is coverage improvement at the time of
It's the instruction per cycle, which is directly correlated to coverage. This is just the runtime. That gives you that. Okay, so all good then. I should stop the talk now, but still we are trying, right? So what happened with this proposal is our ideal L1. If we count the ideal L1 configuration. Oh, sorry. This one?
Yeah.
Huh. Yes.
So are you selecting that you are getting majority of those tiny prefetchers, or how are you selecting the?
So this is like a cricket team. I wrote a blog about it actually in the form of that. So depending on the pitch condition, you decide, who will be your batsman.
Who will be so depending upon the prefetching history, like
depending on the access pattern, memory access pattern is the key.
Is this access pattern like how?
It's pretty reactive. It's pretty agile. Looks at past K accesses based on that. Yeah. So just to connect all the dots, this guy gets 45%. But if you do ideal L1 performance, it will be 60%. So still 15% to go. Okay. That means still I can work on it. But you can say, okay, 15% is it's worth exploring, blah, blah, blah. So remember, this was taught from AMD. The AMD Gen 3 to Gen 4, they got just 13% uplift in few years, right? And that 13% came from multiple ideas, not only a single idea, right? And this is one microarchitecture idea, which is called prefetching. This will contribute to few XYG performance improvement, right? This is something I would like to stress more and more, because people assume, Microarchitectures are what's the big deal? 2%, 3% here and there, right? So depending on your taste, you pick one of these, right? So for the I think all of you have read all the things. So let's move on. Now coming back to the research question. The question is we need to get better performance because our L1 hit rate is still not 100%. Okay, and there is still headroom for 15%. You have a question? Sorry. Can you come again? I don't get it. Why testing comes into the picture?
To measure.
Oh yeah, I agree. I'm not saying whatever we are doing is sacrosanct. Okay. So I'm saying assuming you are the Intel, you are the MD of this world, and you are getting 2% from my idea, then that will give you extra few dollars or few millions of dollars, depending on how the market situation evolves, right? So yeah.
I think that isn't this noise?
Yeah, so there is a noise. You can always say that I always listen to those. So the answer is yes and no, right? So see, my job as an academician is to push the limits. Then you give it to industry folks. Industry folks will decide whether it's a noise or it's actually the 2%, right? Yeah. Based on last few years, it looks like it's not noise. Okay, fortunately. Okay, so coming back to the research problem. So it's a game of accuracy and coverage if you want to achieve your dream of 100% L1 hit rate. And as I have already explained, coverage is actually what fraction of misses you are converting into hits, and accuracy is what fraction of preface that you have generated, they are actually accurate, right? So the IISc paper that we talked about, though it improves the performance beating state of the art, it has an accuracy of 60%. What does it mean? It means 40% of the prefacing requests are useless. They are just going to DRAM, taking all the bandwidth without improving the performance, right? Now, this is a question that we asked sometime around 2021, COVID time, nothing to do, right? So the question is, can we design a prefetcher that provides high coverage? It has to beat the IISc bouquet idea, but at the same time, it should provide high accuracy. Okay, and there's a direct correlation between accuracy and energy efficiency. Devasi talked about it at a high level. So if you are doing useless work, you are consuming more power in your chip, right? So this adds up to your power budget at the end of the day, right? So we need a highly accurate and still aggressive prefetcher that can give a sweet spot in terms of everything. Any questions before I jump to the idea part?
Let's say big improved, but at the cost of something which could have been a hit will come a miss.
Possible. Yeah. So all the interactions are possible.
Yeah. So is there a way to quantify that?
Yeah. Any other questions?
So is there some overhead in running the prefetcher in terms of?
No. This guy doesn't come in your critical paths. The program is running as usual. Caches, memory, as usual things are going on. This guy is sitting beside the cache, helping you, right? So it's not part of your primary family that you have of caches and memory. Energy-wise, it will, depending on the size and what computations you are doing, right?
So because of the prefetcher, will the cache always be full?
Because of the prefetcher, will the cache always be full? The answer is yes and no, depending on the memory access pattern. Okay, so the applications that we are talking about, mostly they demand MBs or GBs of data. So anyway, they will be full, irrespective of prefetcher. Okay. If you have a pretty tiny application that demands just 2 KB, 4 KB, or maybe hundreds of KBs, right? Then L2, L3 won't be full, or they will be full with some stale data, right? But the short answer is yes, it will be full. Any other questions?
Does replacement policy has a role in this one?
Yes, replacement policy will have a role provided your prefetcher is inaccurate.
No.
Yes, if it is accurate, then indirect, it's like your prefetcher is similar to your processor, right? Your prefetcher knows what the processor wants, so everything is all good. But if it is inaccurate, that means you are bringing inaccurate cache lines, and you may kick out something useful, right? But it used to be a problem 10 years before when the accuracy of prefetchers used to be below 40%, right? So you bring more and more useless blocks, kicking out useful blocks, right? Yeah.
This one, studies were done on trace-driven simulations.
Yeah, this is trace-driven simulation because what happened in microarchitecture community is everyone came up with their own simulators, and finally no one knows where exactly we are moving to. So thankfully, Intel and few folks from University of Texas and others from ARM and all, they actually joined together and came up with a trace-based simulator, and then provided all the traces, industry traces and all, the traces that are already there, right? So that now we have a playground, a fair playground where everyone can play with, and everything is reproducible. That's more important. Okay. Okay. So let's move on. So the problem at hand is providing high hit rate at L1D cache. So the approach that we took is pretty simple. The approach is, if this is my L1 cache, I'm getting a request to address X. What should I add to this address X and prefetch so that it will be a hit in the future, right? And this D, or the addition that we are going to do, is called the delta. Okay, so what should be the delta that we should add with your memory access and prefetch? So once you get your prefetch delta, you send it to L2 cache. If it is there in L2 cache, it will get it. If it is not, it will go to LNC DRAM, and finally it will come out from the DRAM. Okay. Now the second observations that we found, this is not an exact code, but a code snippet which is well enough to understand what I'm going to talk about. The deltas are different depending on the load instruction. So how many of you know assembly language programming? I'm flattered. Okay, so if you look at assembly, this particular array access will be one load. This will be another load. Okay, and if you look at this particular load instruction, the access pattern is pretty simple, right? C0, C1, C2 kind of. But here there is a modulo 4. So now if I have to design a prefetcher which adds a delta, this delta should be specific to the instruction. I can't have a delta that is global to my entire program, right? Okay. So the next insight that we have is, for every node, we should learn the delta, and because the delta behaviors are different. Okay. So this is something that is pretty famous in architecture community. So this is a benchmark called MCF, which is famous for its notorious behavior at the memory hierarchy. And if you look at this plot, so the way to look at this plot is y-axis shows the best delta, and the other side you have different coverage that you get when you select these deltas. Okay. So the insight that I showed in the previous slide, I said for every load instruction, the deltas are different. But if I just go for a global delta, you can see, for this application, your prefetcher will pick something of 62, but that doesn't provide the best coverage. Look at the density of the color, right? So just to motivate further that we need to have per load instruction delta so that you can understand the heterogeneity in memory access patterns. Okay, so where exactly the prefetchers fail, which are already there in our commercial machines. So if you have a simple for loop like this, you get a strides of +1, +1, +1. If I tell you design a prefetcher for this kind of for loop, what will be the prefetcher? Sorry? Yeah, we just add +1, right? So this is all good. What about this one? What do we do? We can do many things. That's our job as researchers, right?
You could do +2.
I could do?
You could do +2 and then you'll get price.
Okay, probabilistic. You say, okay, I'll actually throw a coin and decide +2, right? At least there is some hope, right? So why it happens? The code is same, right? I haven't changed the code. But the difference here is this is actually in-order processor. Remember the first slide where I assumed things are actually coming into the processor in order and they are getting executed in a completely out of order way. But for this example, I'm assuming we have an in-order processor. So the instructions are also coming in order. Okay, so that's why you are seeing this regularity. Whatever you see as a programmer, the processor is also seeing the same thing, right? But the real processor are out of order processors. So they don't care. If they find opportunity to improve parallelism among instructions, they just go for it, as long as they're independent. In this case, they are independent, right? So again, same problem, Bangalore traffic. Yeah, same thing. You can't say about Mumbai, right? I think today, in today's news, it came that Bangalore is the second worst city in terms of traffic. No one else. Right? So, see, same. Bangalore, Mumbai, Delhi, all the big cities in India, to make it clear. Right? So then we need a prefetcher which actually takes care of all this dynamics. Irrespective of the processor, the prefetcher should provide high coverage and accuracy. Right? So this is what we came up with. We call it BUTTI. It came in Micro 22. And the idea is no instruction. We already discussed why we need it. We are finding out the best request time aggregator delta. It's a pretty heavy statement. Let's go for one word at a time. So let's first understand why time. Why time is important for prefetching. Any guess?
Data should be there in the cache before we actually.
Yeah, that will be the ideal case, right? Whatever the processor needs, the data should be there before time, so that you'll get a cache hit. Okay. Anything? Are you missing anything in terms of the notion of time? Any random guess? Educated guess? Okay. So we have been assuming that the time to fetch the data from outer levels of memory and from memory is kind of constant, which is not the case. Okay. So this is actually a number on a real system for a memory intensive application. So you will find that the time to get the data into L1 can vary from 22 cycles to 2000 cycles. Okay. And each load has different time to get the data into the cache. There are tons of issues like locality, reuse, as Devasai talked about, queuing delay and whatnot, right? Finally, it's out of order memory hierarchy, right? Which means you have out of order processor and you have out of order memory system. What else you want, right? So that's the best playground to play with and still deliver high performance, right? So to understand the notion of time, let's look at this example where this timeline shows the memory accesses, which are addresses, okay? Like 2, 5, 7, 10, 12, 15. So if my goal is to make sure this address 15 gets a hit, when should I prefetch? So if I prefetch when I get a request to address 12, it's actually too late. Why? Because it shows to get the address 15, it has to be triggered at least before this point. Which means I should either trigger my prefetch request when I got a request to 2 or to 5. And if I use these two as the address of interest, then the triggers or the deltas will be 2 plus 13, 15 or 5 plus 10, 15. Okay? If I do prefetching after this, it will be accurate, but it will be late. So then it's not useful. It's not helping me, right? So that's why time is crucial. The next keyword is aggregate of deltas. Let's try to understand this. Pretty simple example here, memory accesses. Again, strides of 1. So based on the previous slide, what you will do if you want to make this address 12 hit, you have to look at what is the latency or fetch latency to get the address 12 into cache. Depending on the fetch latency, you decide whether to prefetch from here or prefetch from here, right? So look at this particular access stream that we just discussed about Bangalore traffic or Mumbai traffic, right? So you have 0, 1, 4, 9, 10, 13, 18. If you just look at it straight away, you say, oh, there is no access pattern here, right? But hang on, you'll see that there are strides which are variable in nature, but they recur, right? So 1, then 1 to 4, 3, 4 to 9, 5. So there's a sequence of +1, +3, 5 continuously recurring. So now what you can do, instead of looking at deltas as difference between just two addresses, you add all these strides. Right? So if I add all these strides, I get 9. Right? And if I get 9, every time I enter request to 0, I refresh 9. 1, refresh 10, 4, 13, 9, 18, 10, 19, like that. I'll be able to cover all the misses, even if it is irregular. Okay? So with that, we came up with this prefetcher that actually makes a guarantee that as long as we are finding out timely deltas which are coming to cache on time, and they provide the best local coverage, meaning per load instruction, if they are covering most of the misses, then it will contribute to the global accuracy. So that was our goal when we started, right? We wanted to design a prefetcher with high accuracy because energy efficiency and other things are also important. Right? So I won't go into the detail of this slide. If Sumit puts it on the workshop page, then it's fine. This just shows how it works. So we have different addresses. We just record their timestamps, and then for each delta, we look at their per load instruction coverage. Based on that, we decide what to prefetch. If you don't understand it, perfectly fine. Insights are most important, and the takeaway message is important. So what it provides finally, it actually provides high coverage, high accuracy, low traffic and energy, and low storage overhead. Can someone guess what kind of accuracy this guy or this prefetcher provides? Previous was 60. 62, okay. I think the microarchitecture improvements motivated you. Any other guess? 90. You can say 100. That will be done, no? Okay, the big deal is it outperforms the previous prefetcher by 3.5%, right? And accuracy is almost 90%. Okay? But the key here is this high accuracy is not at the cost of coverage because you are getting 3.5% improvement. Right? So the 45 now become 48.5, energy improved up to 90%, still 12% to go. Okay? Any questions?
So the latency to get into L1 is because whether the data is in L2 or not. You had from 25 seconds to 2000.
It's a multi-core system. There are like multiple things happening at different queues. Depending on how those requests are getting scheduled at different layers of memory, you may get pretty high latency or low latency.
Yeah, so my question is a bit naive question.
Yeah, good.
So one is that how does the prefetcher know that what should be the stride? Does it just wait and see that what should
Yeah.
be the
So
stride?
as I said, right, it looks at the past. Right? So it will look at the past k accesses, and in this case, past k accesses of that particular node, and then speculate about the next k accesses of that particular node. Right?
Particular node?
As I showed you, right, the for loop with two loads, Ci and Di, deltas are different. So for each load instruction, we are training the loads differently. Otherwise, if we just go for the global delta that we discussed, it will be the entire program, but the accuracy will drop. Different loads, yes.
K-axis is that is
This is fixed, at least for this design, it's fixed.
This is assuming that the workload runs for a while on this CPU without being thrown off.
Okay, define thrown out.
Context switches.
Context switches, yeah. So this we thought about it. Context switches, if you look at it, their frequency will be in microseconds. Right? Here we are dealing with nanoseconds. Right? So even if you do context switch once in few microseconds, it will take few time, few cycles to rebuild its intelligence, and then start doing based on the application memory access pattern. Right? Okay. Any further questions, or I'll go to the last part of the talk. Okay, so now we have a prefetcher which is highly accurate, 90% accuracy, beats all the state-of-the-art prefetcher, all good. But then I started asking this question sometime in 2021, that what about server processors, right? Where you have 64 threads, 128 threads running concurrently on a many-core system. Okay, when I say many-core, I am referring to 64 core or 128 core system, Okay. So let's digest this picture. So you have a 64 core system. Each core has its own private L1, L2 cache. L3 cache is kind of distributed, but still shared. Okay. And the key point here to note is the DRAMs that you are seeing, right? The green color rectangular ones, they are actually limited in number. Although number of cores are 64, but the DIMMs or the DRAM chips are just 8 in number. Okay, which means there are only 8 ways in which these 64 cores can go to memory and get the data. Right? So this is like if you have 64 cores running in an expressway, but the expressway has only 8 lanes. Right? Imagine what will happen. Same thing happens here. Okay, so we understood BERT. We just discussed this is the highly accurate prefetcher. So the way to look at this plot is y-axis shows performance improvement. Anything more than 1 is improvement. 1.1 meaning 10%. 1.3 or 3.5 is 35%. Okay. So if I have a 64 core system having BERT prefetcher with 64 channels or 64 DRAMs, then I get 35% improvement. All good. Okay. But if I change that 64 to 8, then forget about improvement. I get degradation. It is below 1. Okay. Which means now there is a gap of 16% that I have to nullify just to make sure it delivers performance similar to no prefetching. The better idea for the servers is just don't do prefetching. That's what all the server processors used to do. Okay. Is the problem clear? Why it happens? Or whether, okay, you can ask that, okay, whether this is noise or cooked up? No. This is actually some of the data, actually real system data. Although BERT prefetcher is not there in the real system. So why it happens? Because you have only minimum number of channels for 64 cores. So the bandwidth per core drops significantly. Okay. So which means now it's a bottleneck that we start about, right? The talk was all about the bottleneck. So now you have a bottleneck in terms of bandwidth, not in terms of latency. So the example that I talked about in terms of expressway, right? But to make it more interesting, I hope this will explain the problem in a more clear way, right? If you provide 64 channels, all are good, no issue, all the cores are getting the data pretty fast. But if you have only 8 channels, this is what happens, right? And bandwidth is a shared resource, right? It has, let's say, 50 Gbps, 25 Gbps, 100 Gbps, which is shared across all the cores, right? And on top of your applications, now prefetchers are sending their request, which is making it worse, right? Even if your prefetcher is 90% accurate, so they are also sending requests, right? So the simple non-solution, don't do prefetching, right? At least you will save the 16% degradation that you are getting, right? But then what's the point of doing research if you say don't do prefetching, right? So to understand the problem in a more detailed way, the germ of the problem is when you have reduction in bandwidth, it manifests itself into a latency problem, right? If you have a 4-way lane and you have 60 cars to cross, eventually it will become a latency problem. It will take more time, right? So what's the goal now? The goal is not to prefetch. The goal is just to reduce traffic, not Bangalore traffic, memory traffic, right? First idea, right? Drop the inaccurate prefetch request. Prefetch requests that are not accurate, drop them. At least it will save you 10% if you are using the vertic prefetch. Idea 2, prefetch loads that are critical. I will define what is critical at a high level, but in the context of road traffic, you can assume, ambulance is more critical than a normal car. Right? So if you're stuck in traffic, then you have to take care of the ambulance and not the normal cars that you see. Okay, look at the idea 1. It's not new. People have been trying around this idea. So the idea is whenever your prefetcher accuracy is poor, below a threshold, don't do prefetching or prefetch conservatively. Okay, but here I propose a prefetcher with accuracy of 90%. So it passes all the threshold. It will do prefetching. So this idea won't work. Idea 2, it's called you decide or you kind of train or predict which particular memory accesses will be critical, and based on that you tell your prefetcher go and prefetch those critical nodes. Okay. By the way, one of the work is actually done by Govind in 2008, long back, right? So you can assume that, or you can see it, right? The timeline, IISc 2001 till 22. So it's been 20 years of research trying to find out critical loads of the memory system, right? So I'll give you a 10,000 feet view of critical load. Remember this slide I started in the beginning of the talk. So now if I have to, introduce the notion of criticality, then this load actually satisfies the definition of criticality because this guy takes more time. So I should try to prefetch this load. For these two loads, it's okay. Anyway, I'm getting a hit in L1 and L3. Okay. So which means now my traffic will go down. I'll just send a prefetch request for this one. For this two, I won't. Okay. But even these ideas don't work for 64 core system with 8 DRAM channels. Why? So the first idea, as I was talking about, they just look at prefetch accuracy, below threshold, don't do anything. It won't work. Second idea, that criticality that I talked about, so they actually assume once a load becomes critical, they're always critical. Okay? So you imagine a situation if inside ambulance the patients are not there. That's happened in India at least, right? So then the traffic will go for a toss. Key insight 3, this is new. In the presence of prefetcher, remember prefetcher is a latency hiding technique that's trying to convert L3 hits to L1 hits or memory access to L1 hits. In the presence of prefetcher, some of the critical loads may become non-critical because prefetcher is actually helping them, and non-critical can suddenly become critical. So this rigid definition of, okay, once it becomes critical, it's always critical, it doesn't help. Okay. So this is just a plot to show that there are load instructions with dynamic behavior. So D here is actually the dynamic behavior, which means a particular load, even if it is critical once in a while, it's not critical all the time. But the S here is actually static, which means once it is critical, it's always critical. Okay. So we found that 50% of the loads are actually dynamic in nature. That's why the previous ideas are not working. So what we proposed, so again in the interest of time, I'll just give a summary. We came up with a predictor that actually looks at it's a bit of a compiler language, bit of control flow and data flow of all the memory accesses, and try to ask if this is the control flow and data flow of the application, will this memory access become a critical load in the presence of prefetcher? That's key. Okay. And that is the criticality part. And then we also looked at accuracy of a prefetcher, but not for the entire prefetcher, but for each load instruction, you need to understand whether the accuracy for that load is high. Okay. And the final idea is you prefetch only if that load is critical, as per our definition, and the prefetcher can prefetch it accurately. Okay. So that's what this proposal is. In one slide, this appeared in Micro 23. So you prefetch loads which are either critical and prefetched accurately by the prefetcher. So if you have a prefetcher that can prefetch things accurately, but it's not critical, don't do that. Don't prefetch. Similarly, these are critical loads, but the prefetcher is not intelligent enough to prefetch them. Again, don't do anything. Right? So with that, what happened? We reduced the traffic by 50%. In some of the cases, 99%. So basically, you are doing nothing, right? You are doing no prefetching, right? So this is a pretty interesting application that have pretty few, prefetch requests generated because it doesn't pass the criticality definition. Okay. With that, what happened? We said with 8 channels, 64 cores, we get a 16% dip. Now it became 88% improvement. So overall, there's a 24% gap. Okay. So this idea actually came up as top chips achievement in 2023. This was one entry, at least from Indian academia, that is the feel-good factor to see here. Okay. So the take-home message, I'll wrap it up in few seconds. So the first part of the talk said you can actually prefetch aggressively, but with light prefetchers, pretty lightweight prefetchers at L1. Then we found energy efficiency is an issue. You can't just say, okay, I want performance, so go and prefetch bang, 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 right? So we designed accurate prefetcher. So far, the accurate in the entire community, 90% accurate. It beats the previous one. Finally, when it comes to servers, we found all the prefetchers are useless. In fact, they are degrading performance. Forget about improvement. So you prefetch only the critical loads, but provided they are accurate. Okay. What next? Maybe next workshop. So with that, I'll stop. So this is my group at IIT Bombay. Most of the members are 1 year, 1.5 year old. Few undergraduates, few MTech, MS students, and few PhDs. So we do microarchitecture research with S and P in focus, S for security, P for performance. Okay. So with that, thanks for your time and thanks to me. Any questions? I think I finished before time. Yeah. So that's the good part of microarchitects. Any questions for the last part of the talk? Because we covered the first two parts anyway. No? Okay. Sure.
What are your criteria for criticality? Criticality?
It was a bit tricky. So, maybe you can take it offline. Okay. So the 10,000 feet view that I have given you that, okay, any long latency load is critical, that's not correct. Fundamentally. Yeah. So it looks at many things and then finally it says, okay, if it respects all these things, then it becomes critical. Okay. So just to give you a high level example, if there is a branch, that branch is taken, within that if there are loads, those loads are they are also critical. You do tons of checks and then finally, if all the checks satisfy, then you say it's critical. It's pretty restrictive. Yeah.
So you mentioned that L1 load taking 300 cycles, and as a result, that reorder buffer taking up that slot, right? Why is that a problem?
No, retiring bottleneck, why is it a problem?
Yeah, retired. Yeah, what is retirement?
Because you have to retire in order, right?
Correct. So basically, it means you need to have bigger.
Bigger reorder buffer is not free. Right? So
you have a limit.
No, see, even if you have a bigger reorder buffer, this problem may become even a bigger problem, depending on your program. So I'll give you a simple example. Let's say you have a branch condition, and let's say there is a branch and load which are dependent, right? So if your ROB size is pretty huge, let me give you a hypothetical number of 1,000 instructions, right? In the worst case, you have to squash 1,000 instructions if you are going the wrong path, right? And in the same time, let's say your prefetcher is doing all the intelligent things, assuming I am doing all good, bringing data into my memory hierarchy, they're all useless now, right? So there's a trade-off. So sure, if I have a better or a larger ROB, it will give me opportunity for more parallelism, right? Yeah, but it has its own trade-off. Okay, I guess we are done.
Okay, let's thank Vishwa for an excellent talk. Here's a small memento from the organizers.
From organizers. It's great. नीचे अभी ठीक है.
Thanks. Okay, so the final talk in the session before we have the next is by Professor Govind Rajan of Isomar Department at IISc. So Govind has done his BE and his PhD from IISc way back in 1985 or something, and then he joined the faculty at IISc. And for many years he was looking after the Supercomputer Education Research Center on campus. And Govind is well known for his work in in various aspects of architecture, high performance computing, compiler techniques. And he's also one of the most, despite being one of the most senior professors, he's also one of the most prolific publishers in our department. And he has more than 135 publications to his credit. So today Govind will tell us about compiling and machine learning. Over to you, Govind.
Thank you.
Please welcome.
So thanks, Deepak, for the introduction. Not sure whether I'm still a prolific publisher, but I probably was some time ago. Okay, so if you just give me a minute, I will get things set up. Okay, so thanks to the organizers for inviting me to give the talk. I'm not sure how much you heard about compilers in this workshop, so I'll talk a little bit about that, but again, just based on popular demand, I will actually link it with machine learning, right? So what's a compiler? Compiler takes a high-level language and then converts it for a target machine into a low-level language, right? And typically, a compiler consists of a front end. The front end takes the program input or whatever, converts it into some intermediate representation, and that intermediate representation is later converted into the target architecture's machine code, right? All the slides will be available, so don't try to capture it every now and then, because sometimes you will see some overlapping diagrams on top of that. It may not be very exciting, right? I'll actually put the PowerPoint presentation with all the animation so that you can actually look at it if you want to at a later point in time. Okay, so what is the how many languages and possibly many target architectures, right? Do we build one for each pair of input language, or one for each high-level language and one for the target architecture, or is there a better way of doing this? Of course, there is a better way of doing this. You write different front ends for each of these languages, and you write different backends for each of these target architectures, and then the common intermediate representation is your common middle ground. So basically, the front end takes these high-level languages and then converts it into this common intermediate representation, and then from the common intermediate representation, you use specific backend to target for a different target architecture. This is all fine. This is all old stuff, right? And people have been talking about it from the 70s, 60s, or 70s. And a lot of things has already been done by the late 90s. That is when I was a graduate student, or when I finished my graduate program and things like that. So one might ask the question, right? What's so exciting about compilers? Why do we even talk about it? In the workshop, it talks about the present and the future. Is there any future for compilers? Yeah, of course, yeah. A lot of positivity, optimism. Thank you. Okay. So we really have to answer these questions, right? Isn't this very old-fashioned, completely saturated, right? Why would the industry care about compiler designers? Okay, the questions that are often being asked. And I think prior to me, a couple of speakers from the architecture area spoke about, and they have nice things to brag about, like the Moore's law, where the performance doubles every 18 months, and so on and so forth. I do have a similar law here, right? What is called the Propsting's law, right? It says that the improvement due to compiler doubles every 18 years. So just wait for 18 years, your performance with compiler techniques will double. Right? Given this skepticism, thanks, Rahul is coming later. I already showed about the skepticism in compilers. Okay, doesn't matter. Okay, is there any purpose in doing anything in compilers? Right? Of course, I don't want to end this in this note. So let's talk about how compilers are getting excited. Right? You no longer talk about just these languages. You talk about these different kinds of frameworks, right? And compiling for these frameworks. And here you can see TensorFlow, PyTorch, data analytics frameworks like Spark and other things. Of course, all the traditional languages plus all the dynamic languages as well, and many domain-specific languages as well. Now you talk about compiling these things to different target architectures, and the target architectures are no longer somewhat homogeneous like this CPUs, right? You have different kinds of target architectures, like you have the CPU cores, you have the TPUs, right? You have the TPUs, you have the GPUs, you have crypto processors, you have the neural processing units, and so on and so forth. Right now, the whole thing is getting exciting, right? Because you no longer talk about only those traditional languages and compiling them into CPU code. You talk about a variety of target architecture and oftentimes supporting many of them together in a synergistic way. That's something that's new, and that's something that requires more work, right? So compiler design is becoming more and more challenging, okay, and requires knowledge of many disciplines, including architecture, software engineering, and other things. And of course, sometime or later, we have to fix this skepticism from the Probst's law, right? We have to say we can do something better. Okay. All right. So let's talk about compiler research meeting machine learning, right? First, we will talk about how machine learning can help in compiler design. I'll give you a few examples of this, some work that we have done, and then later I will talk about the other aspect, how compiler design can speed up machine learning applications. So both sides we will talk about, right, very briefly. Okay, so here are some examples. First of all, here are some reasons or some places where machine learning could be very useful. When you talk about different compiler optimizations, right, these optimizations actually built to improve the performance. But one thing that happens is that it's not that always all of these optimizations improve performance or guarantee performance improvement. Some can actually result in a negative performance, right? And some of these optimizations require certain parameter values to be set correctly meaning an appropriate parameter value would give you a better performance improvement, where some other parameter value could either cause a degradation in performance or no improvement in performance. One example of such a parameter is unroll factor, right? What should be the unroll factor for a loop? And if you choose the correct unroll factor, you would probably get a very good performance. And a wrong unroll factor sometimes may end up in giving you negative performance. There are many optimizations in the compiler. You may want to use a subset of them in order for you to improve the performance of your code. And that subset may vary from code to code or from program to program. And it's often harder to find that out. And there is an ordering between these different optimizations. For example, when we talk about compilers, we talk about things like instruction scheduling, register allocation, and so on. And some of these optimizations happen one after the other. And the order in which they happen also influence the performance. So for different applications, doing, for example, register allocation first and then instruction scheduling may be better, whereas for some other program, the other way around might be better. So how do we decide in what order to apply these optimizations so that performance benefit will be done? And again, one can talk about vectorization, what should be the vector length, and if you're interleaving different vector instructions together, what should be the interleaving factor, and so on and so forth. So there are many decisions that one needs to take when you are using your compiler optimization. Simply put, right, if you try to compile your program with, let's say, with a -O2 optimization, execute the code, versus put, let's say, a -O3 optimization and execute the same code, right? It's not always guaranteed that the O3 optimization will give you better performance improvement. Sometimes it can perform worse than O2, right? And this may change from program to program. So the question is, how do we ensure that whatever optimizations that we put in or whatever optimizations that we want to be applied always result in better performance, right? So one could actually use machine learning models to understand this and then come up with the right subset of optimizations that should be performed, the appropriate parameter values like the unroll factor and so on, and can actually get good performance improvement. This work was, I think, there are many aspects of this work, and they have been pursued, I think, since 2004-2005 time frame. A lot of it has been published in compiler conferences like compiler code generation optimization conferences and so on and so forth. Okay. I'll also talk about another aspect of compiler optimization, particularly this one deals with the GPUs, graphics processing unit. And when you have a mix of CPU cores and GPU cores, and you have your program, and you divide your program into different tasks, and if the compiler has to decide which task to be executed on the CPU cores and which task to be executed on the CPU cores, many a times this decision is easy, but sometimes this decision could be tricky, and that depends on the nature of computation which is being performed by the task and the other loads that exist on the system. And in these cases, again, deciding something could become harder, and machine learning could come helpful for that. In a similar way, when you are talking about compiling your code for GPUs, and let's say if this code is in some kind of OpenCL kind of a language, then there are certain optimizations that you can do where you can actually coarsen the work done by a single thread, and to what extent you have to coarsen can also be decided by machine learning methods. And again, there are works which have been published in this case, and there are many, many more. So these are just some examples of work where machine learning and machine learning models can help to predict what optimizations to use, what parameter values to choose, and so on and so forth. Let's go and talk about some specific work that my group has done. And here we are looking at identifying best performing loop orders, right, for loop tests. Right? Why do we care about this? Today, when you want to execute, let's say, a loop nest, and when you want to execute it on a many-core or a multi-core processor, there are different levels of parallelism that you can exploit. Right? Each core has some kind of an AVX instruction support, right? Therefore, you could exploit vectorization or data level parallelism within a single core. And there are multiple cores in your processors, and therefore you can exploit task level parallelism as well. Okay, and of course you have this big memory hierarchy which Viswa talked about. And if your code is not properly, if the code layout is such a way that it doesn't exploit the cache hierarchy properly, or if the locality is not exploited properly, then that could result in poor performance, and therefore one should actually care about locality as well, right? And enabling and disabling prefetching itself could make a difference. It's not that always enabling prefetching is going to result in good performance. So is there a way by which we can decide when to enable prefetching and when not to enable prefetching, right? So these are important aspects. So the problem that we have on hand is that given a loop test, is there a way by which we can identify, right, the best performing loop order? I'll tell you what the loop order, what do we mean by the loop order? What is the tie size that we have to use when you try to block these loops, okay? And whether or not to use the prefetching, and what prefetch configurations to use, etc. So is there a way by which we can look at it? First, let's understand what do we mean by different loop orders. Yes.
The previous slide, you have software prefetching.
No, the hardware prefetchers. The hardware prefetchers. So you can, for example, you can disable your L1 prefetcher if you want to. Right?
But do you do anything for software prefetching?
We don't. In this work, we did not. In this work, we did not. Okay. So let's just consider a very simple loop, right? A two-dimensional loop, right? We have a for I loop and a for j loop, and it is doing some computation, right? Now, in order to exploit my cache hierarchy well, right? Oftentimes, what happens is that you tile these loops. You tile this loop, meaning that instead of j going from 0 to, let's say, 1024 or 2048, you make your j go from, you actually tile this in terms of blocks, right? Anybody who has seen this matrix multiplication example, right? Block matrix multiplication example would have actually recall what do I mean by here, right? So instead of making this one loop j going from 0 to 1024 or 2048, you break this into two loops. The inner loop, which is actually what we call as the intra-tile loop, right, goes from, let's say, 0 to some value t. T could be 16 or 32 or whatever small value. And then the outer loop basically takes care of going through each one of these tiles, right? That's what we mean by tiling this loop. I'll show you the example in the next slide, okay? So when you tile this loop, and if you can actually change the loop orders, right? Instead of writing for I is equal to 0 and then for j equal to 0, you can actually interchange the loop orders. You can actually get different loop orders. Let me directly go and then show you the loop orders, then come back and then, okay. So the same loop, now after tiling, you can see that the tile size is T, right? After tiling, we basically have 6 different loop orders, right, that we have, right? The I and j loops are the inter-tile loops, the II and JJ are the intra-tile loops, okay? In this particular example, we always make sure that the inter-tile index comes before the intra-tile index. For example, we don't consider an order in which II comes before I or JJ comes before. It doesn't make sense because it doesn't exploit certain things. But let's not get into this. Even for this simple loop, right? You have possibly 6 different loop orders. If you consider a 3-dimensional loops, you will have 54 such loop orders that are possible, right? Now, which of this loop order will give me a good performance on a given target architecture, right? So that's the question that we want to ask, and then we took some simple examples and then ran it using these 6 different loop orders. And you can see that the performance could, on an average, be as as low as 5 times slower, or can be very slow, as much as 40x slower, right? So if you end up picking the wrong loop order, right, the best loop order here is this one, which is actually the L2 loop order, right? That gives you an execution time of 1x in the normalized scale. Whereas if you choose the wrong loop order for this particular loop, you could actually end up spending 45 time units. Similarly, in this case, right, the best loop order is L3, and the worst loop order has execution times which are 50x worse, right? Therefore, given a particular loop, if the compiler has to automatically decide, I will do this blocking and then I will do this loop interchange transformation, but then which one of the loop orders I have to choose, if it uses some heuristics and ends up using a wrong heuristic, the performance loss could be as worse as, on an average, 5x or maybe even 45x in the worst case, okay, in these loops. Okay, so can we use machine learning models to identify the best possible loop orders, right? That's the question that we ask. And in the first problem that we look at, we assume that the tile size is fixed. The tile size is fixed to 32 based on the average cache size and other things. So we just fix it to 32, right? In the second problem, we look at, supposing I change the tile size, and how do I pick the optimal loop order? Trying to look at both tile size and other things. We also look at the problem of, there is an optimization called unroll and jam, right? Instead of unrolling the innermost loop in a loop nest, I can unroll any of the outer loop levels, and then I can jam them together in order for me to exploit vectorization and other things at the outer level. If I do that, do I get benefit? Should I do unroll and jam or should I not do unroll and jam? Because in some loops, doing unroll and jam gives me performance, whereas in other loops, it gives me performance degradation. Of course, we have not really gone into this particular aspect, which is whether or not to enable the prefetches, because we have some limited handle on this, but we did study with different prefetch configuration how they perform and things like that. Okay, so let me explain what we did in this one. Yeah.
The order, the dependency doesn't matter.
Okay. Okay. So sorry, I skipped over this thing. In all of this, we are basically making sure that the data dependencies that you have are always satisfied. Because if you violate that, then obviously you are not going to have a correct execution, right? We use tools like Poly and Pluto, right, to understand the dependencies and make sure which of these transformations are possible. In this particular case, the loop interchange that we do and the tiling that we do basically ensures that you still preserve all the dependencies. Okay. Again, remember, okay, one other thing that I forgot to mention here, maybe it's a good idea to go back, right? So you have the statement over here, and when you have this loop, right, we exploit vectorization if possible at the innermost level, and we try to exploit parallelism across any of these outer loop levels, whatever that is possible. right? For example, if the loop is parallel in both I dimension and j dimension, which means that it can trivially parallel, which means that all iterations can be executed in parallel. Then in this particular loopness, the jj loop would be vectorized and the I loop, right, would be parallelized. That means that there are many tasks which are executed on these different cores, right? And then within each core, there is vectorization that is being exploited. Okay. For example, let's say that if the loop has a dependency on the jth dimension, that means that different iterations of j cannot be executed in parallel. Then in this particular loop order, right, because the jj dimension, the j and the jj dimension has a dependency, it cannot vectorize this loop. However, it can parallelize this loop because the I dimension is parallel. There is no dependency on the I dimension, right? And of course, for the same loop, you can see that this particular, sorry, not this one, yeah, this particular loop can be vectorized because its innermost loop is II dimension, and this is outer dimension is also parallel. So different loop orders have different things in parallel. So the whole idea is that which one is beneficial. But to answer your question, we have to ensure that all dependencies are satisfied. Okay. So the dependence checking is not a part of the machine learning part. The dependence checking is a part of the compiler tools like things like polyhedral tools like Pluto or Poly. Okay. So we model this problem as a supervised machine learning problem. Okay. And we use handpicked features of the loopness, which include things like dependence, parallelism, whether it's doing a row major, whether it's doing a row major access or a column major access. Okay, number of multidimensional arrays that we have, what kinds of array accesses it has, and so on and so forth. Those are the input features, right? And the output class that we try to predict is one of these 6 classes, L1, L2, or L6. Okay. So we use support vector machine for this classification. We tried other classifications like simple decision trees and so on, but this works better. One of the challenges that we had is that we had not enough loops to train, right, these machine learning models. So we came up with an automatic loop generation mechanism, and then we ran those loops on an architecture and then obtained the data set, classified, labeled them, and then used them for the training set. Okay. And of course, sorry, I mentioned that we use the support vector machine for as a machine learning model, and when we use a large enough training data set, this performs well. But when we use slightly smaller training sets, it doesn't perform as well as this one. Then we said that one could actually do what's called an ensemble prediction, multiple SVM predictors, and then try to take a majority vote of them. Okay, this is the random data dependency graph that we generate in order to generate these training data sets. Probably not very interesting here. Let me skip that. Okay, so when we deploy this method, what we find is that our machine learning method often finds close enough to the best performing loop order, right? We can't always get the best performing loop order, but we are within 10% of the best performing or the optimal loop order, so to say. Right? These are some performance numbers. I'll actually skip. Then compared to competitive methods, we perform something like 1.3x to 1.8x better. Okay, we keep those results and then go to the other. Okay, the second problem that we solve is that, okay, this is good. Once you fix a particular tile size, our machine learning method can actually identify which loop order to use or execute. What happens if I don't fix the tile size, right? So if you look at it, I ran some program with a specific input size 8K, and then 2 different tile sizes, tile size 8 and tile size 16. Right, you can see that in one of them, L2 loop order performs better. In the other one, L3 loop order performs better. This is normalized execution time, so the lower is better. Okay, and it is normalized with respect to the lowest value. So that's why you see 1 here. Right. Now you can see that as the tile size changes, right, even for the same program and for the same input size, right, the loop order could change. right? And the worst thing is that if I use the same loop order and then execute here, right, I could actually incur significant performance loss like 15% or 22%, depending on what's happening, right? Okay, so that's one problem. The other problem is that tile size selection can also significantly affect the performance, right? For the same problem, same input size, we ran different tile sizes and then we ran different loop orders, right? The best performing tile size is 64 for this particular loop order. And the worst performing one, as you can see here, I can quickly look at it, is this one, which is 25. X, maybe there are others that are bad. Okay, but then even if I fix my loop order and then go between different tile sizes, my performance varies significantly. Or if I fix my tile size and then go across different loop orders, there also I have serious performance degradations, right? Therefore, it's actually important not just to fix a particular loop order, but it's also important to select the appropriate tile size. So we again model this problem, right, as a machine learning problem. And then when we try to use something like a support vector machine, it doesn't perform well because now we have too many choices and it leads to poor prediction. So we actually built a hierarchical classifier. I'll show you the hierarchical classifier in the next slide. And then we actually tried to hand tune this model, or we also did something like a systematic exploration of the entire hierarchical space. And again, we used the same handpicked features for our models. This is how the hierarchical model looks like. You can see that at the highest level, we try to predict one of the loop orders into two groups, and then within that, we try to either select some tile sizes and go on, right? This is done with the help of a machine learning expert who told us how to go about doing that. And then, of course, once we got this template, we also tried various possible things and then obtained the best possible hierarchical classifier. So with all of that, we were able to achieve actually within 17% of the best performing loop order using our machine learning models, and it performs about 1.5x better than the other loop models. Okay, now let me spend the next 15 minutes or so trying to talk about the other aspect where we talk about compiler support for machine learning. But before I go into that, are there any quick questions?
So maybe you mentioned one decision tree based approach. Does that help you to get more explainable?
Very good point. Yes. So typically, the decision tree based approaches do help you to get explainable things. But the one that we use did not perform as well as the SVM based models. So we didn't really go into more details about that. But then when you look at the style size and loop order, you really need to go much more than that. So yeah, again, I don't think simple classification models like C4.5 or C5.0 is going to do well, although they have the advantage of explainability. Right.
There's no insight into the what is making these loop orders for these programs
better. Okay, so it's actually it's a fairly complex combination of things. If you again look at compiler literature, these problems are solved using heuristic methods. And typically they say that if you have this kind of a dependency, then this loop order might perform better, and then having this as the outer loop is better, and so on and so forth. They work to a certain extent, right? But then when you have a complex combination of things, they fail. And what these things essentially try to capture, these machine learning models try to actually address, is that complex combination. And that doesn't easily come out in the simple classification-based models, at least to the extent that we tried. Right, yeah, Raghavan?
So the results you're saying 15%, 20%. So
Correct.
is this, how reproducible are they? So are these benchmark sets considered exhaustive by the whole community, or
these are typical two-dimensional loop nests that are being used, benchmarks from the Poly benchmark suite. Okay, they don't cover necessarily all programs, but these are the typical two-dimensional, three-dimensional loops that are being used. Okay, with certain dependencies. Right. So it's not universal for sure, but it is reproducible in the sense that for these kinds of loops, this is what you would expect. Pramod?
the type check is dependent on the cache parameter.
Correct. Cache parameters, and also depends on how many arrays you are accessing and what is your access order and things like that. Right? The numbers that we showed, that the variations that you see among the tile sizes actually happen for the same target architecture, right? Same processor, same cache size. So even that, because different loops, because of different things, it actually changes.
Did you try with systems with different kinds of cache hierarchy?
Okay, so we tried only two different systems. Okay, one is a KNL architecture, and the other one is a Cascade Lake architecture. Right? We haven't tried many things. But again, the cache architectures, the hierarchy itself is very different in them. The KNL has an L3 cache, which is an MC DRAM, which is very large. So to that extent, they are different.
But even the inclusivity and exclusiveness.
Exclusiveness, not sure whether that.
Because the interactions will change, right? Because the different lines of cache.
Possibly, yeah.
And the numbers that you showed is for a many-core system, multi-core system.
It's a multi-core system, yes. So for this Cascade Lake with 32 cores and KNL with 64 cores.
So is it scalable?
We did some studies on increasing and decreasing the number of cores. Right.
What were all the input features for these models?
Okay, I showed you that. So it's actually capturing some of the dependencies in the loop, the number of one-dimensional, two-dimensional arrays, the type of accesses, whether it is row major, column major, and so on. Those are totally about 10 or 12 different features that we capture. Okay, so Sumit, I have another 10 minutes.
Yeah, another 10 minutes.
Thanks. Okay, sorry guys, let's take it deeper. Okay, so let me try to very quickly get into this one. So one hand, we talked about how we can use machine learning models to support compiler design. This work actually talks about how compiler design could be useful in machine learning program executions, right? Because this is just a motivation to say that we need better compilers, better architectures for executing machine learning programs. Okay, let me skip that and then go to things like, when you talk about things like deep neural networks and executing deep neural networks, whether you talk about training or whether you talk about inferencing, there are compiler infrastructures, right, that are there for doing this efficiently. I'm not going to talk about this, and I'm not going to go into the details of this. Just to give you what are these things, for example, TVM is a compiler framework, XLA is another compiler framework, and so on and so forth. They essentially help you to compile programs which are written in TensorFlow or PyTorch and compile it for different target architectures so that your execution of these machine learning models, right, becomes faster. We're not going to talk about these kinds of machine learning models in our work. Rather, we are going to talk about more classical machine learning model, something like decision trees in our work. Okay, so we are essentially talking about ensemble prediction walking decision tree forest. What is a decision tree forest? Typically, it's something like a decision tree like this, in which in each node you essentially evaluate something and then you go on one of these directions. And then, sorry, actually this is a tree, and then in each one of them you go on one of those directions depending on whatever the condition of the node is, and then you kind of come to some conclusions at the end of the decision tree, which is basically the leaf node of the decision tree. And then you kind of have multiple such decision tree, and then you combine this using some kind of a majority voting or averaging or coming up of all of these values, and then decide what should be the decision. That's essentially what the decision tree is about. Okay, and typically you execute this decision trees or decision forest for multiple inputs, basically a batch size which is significantly large. Okay, and a naive walk through the decision tree can be inefficient. I will tell you the reasons for that. Okay, right, a naive walk typically does not exploit vectorization because it walks one node at a time. Right, basically you calculate whether a particular feature's value is greater than some threshold or less than some threshold, and then depending on that you go to the left or right of the tree, and then you walk further down and so on and so forth. So typically they do not exploit vectorization. Another thing is that there's a lot of dependency. There is a branch prediction, and then you follow that, there are other stalls that you incur because of that. Okay, and the memory access could become very inefficient because this would kind of cost you irregular access in memory, right? So these are some of the problems with the decision tree walk. So we proposed a framework called Treebeard, which is basically an optimizing compiler for decision tree based machine learning inference. Okay, as I mentioned earlier, a decision tree is going to look like this. At each node, you are going to actually test one of the features and then see whether it is greater than or less than some threshold. And if it is less, you go to one side, greater, you go to the other side. Okay. And a decision tree ensemble is basically a forest or a collection of these trees, and then you walk all of them, and then you aggregate the results of this walk. Okay. This basically says that this is popular. This is in many of the executions that happen. There's a significant percentage of work that is still using decision trees. Although we may think that neural networks are the most popular ones, decision trees are equally popular. That's what it says. Let's keep that. Okay. So if you look at this, essentially, if I have, let's say, a forest consisting of 3 trees, then any walk through the decision forest is essentially predicting this, and that in turn turns out to be a code like this, where for each input in your batch and for each tree in the forest, you basically walk the decision tree. And walking the decision tree is one node at a time, remember that. Okay? And then for each tree, you basically collect what is the prediction, and then you somehow aggregate those predictions and then tell you for this particular batch, this is the output or this is the prediction. And for each one of the inputs in your batch, you do the prediction. As you can see, there are opportunities here already for you to parallelize. You can actually parallelize for each input, right? That you can do. But parallelizing this part is going to be tricky, right? So that's something that one needs to be careful about. Okay. In the interest of time, I'm actually going to very quickly get into what we have done. So let me just quickly tell you, as I mentioned here, right? It has irregular memory access, and therefore there could be stalls. Okay, it does not use all your vectorization and other things, and there are dependencies and branching, as I have mentioned earlier. So what we propose here is that we propose an extensible compiler framework using this multi-level intermediate representation. And what we do is that we take the decision tree for a score, and then we essentially come up with a multi-level IR, which helps us to optimize. And what we mean by this multi-level IR is that at the highest level, okay, we do certain optimizations, which are optimizations at the tree level. And then in the mid-level, we basically decide on how to traverse this code. And then at the low level, we decide on how to vectorize the code. Again, when we try to vectorize the code, we basically try to generate, in this particular case, we try to generate LLVM IR. And then the LLVM IR in turn generates the specific vector code for the target architecture. We built this entire compiler framework, right? And then used it to execute on multi-core CPUs and showed significant improvement in performance. Okay, so I may not have time to go through all of them. So let me just quickly show you that what are the high-level optimizations that we do. So one of the optimizations that we do at the highest level is to take a decision tree and then tile it. Just like the way we tile the loop, here we tile the tree. And when you tile the tree, you can actually execute all of these nodes in parallel. And even though there is a dependency between the nodes, what we do is that we execute all of them in parallel and then decide which one of the 4 paths it has to take, right? That we can do. So we do some additional computation, but then we do all of these computations together. So that's one thing that we do. And there are some interesting ways in terms of how you can do the tiling of the trees and so on. I do not have time to go into that, so I'll skip that part. Okay. The second thing that we do is that we can order the tails in such a way that when you talk about either multiple batches or multiple trees being walked together, right? It would be beneficial to have tiles of the same form coming one after the other because it exploits certain levels of locality. So we can actually reorder these different trees. For example, it's beneficial to reorder tree 3 before tree 2 and then execute them because it exploits certain levels of locality and so on. And then, of course, these leaf nodes have some connotations, and therefore it's better to have all the leaf nodes at the same level. Therefore, we could kind of introduce some padding, right? And then we do that in order to generate better code for that. In the mid-level IR, we basically generate different forms of loop traversals. Again, this is more like loop ordering, whether you traverse the loop in such a way that for each input in your batch and then for each tree you do, or the other way around, for each tree and then for each input in your batch. So which is beneficial and things like that. And then we also do some levels of unrolling. Again, we do unroll and jam and other things, other optimization here at the mid-level. Okay, and this helps us to basically identify vectorizable code and we vectorize it. So these are some of the other optimizations that I talk about. We can do some levels of repealing, memory layout optimizations, and so on. Okay, and we evaluate this on different decision tree ensembles and show significant performance improvement. Okay. Skip all of this and then just look at this particular thing. So compared to the state of the art, we basically are able to execute decision tree forest on an 8-core multiprocessor system using 2.6x or 4.7x better. Right? That's essentially what we do. Now, using the same framework, we can now generate code for GPUs, graphics processing units. That's the current ongoing work that we talk about. So here, much of the front end or much of the higher level, that is the high-level intermediate representations remain the same. More work is actually needed on the lower end. That's essentially what it is. And this has some interesting angles to it in terms of talking about some scheduling languages for how to schedule these different groups and so on, how to do reduction in GPUs and so on, which again lead to some good compiler optimizations. Okay, so that's the other part. Maybe I'll just stop with that. With acknowledgements to all my students. Thank you very much. If you have more questions, I would be happy to take them offline.
Yeah, how does these three methods compare against extremely random trees?
Extremely random tree meaning?
Like they're called extra trees, and it's an ensemble model known for its extremely rapid inference.
Okay, we haven't possibly tested that. I don't know much about that, but in general, this is this works for any decision tree forest. Okay, this doesn't necessarily look at, well, there are some tree specific optimizations that we can do in our compiler framework, but it works in general for any tree. I don't have specific numbers in terms of how it performs for those trees, but yes, it works in general.
Thanks.
Any other questions? Okay. Thank you.
Okay, so maybe in the interest of time, maybe we can wind up the talk and just like to give this memento to go and
Thank you.
Thank you. Thanks, Varun. Okay, now hand over to Sumit for the.
Thanks, Deepak, for chairing the session. I think that ends the talk. So our next thing is the interaction with the research scholars. I guess they're already here. Maybe we can set up by the time we are coming. So where are they? There's a QR code. First, go to the next one. Yes. So meanwhile, I have already posted this QR code for the feedback. So while we are setting up the stage, you can scan this QR code for feedback. So far, I think only 10 people gave the feedback, but I expect more. And yeah, there are some questions like how was the arrangements? So you can give feedback till now, and maybe the next arrangements will be bad, so you don't have time or scope to change the feedback. Okay, so people can come. Where are those people? Yeah. So with us, there are 6 people, Athar, Kanmani, Mohit, Rupasri, Stanley, Arun, Athar. So yeah, please give them a round of applause for making time for this session. I think I'll request one of the, all of you to introduce yourself one by one.
Hi, I'm Stanley, and I'm currently a PhD student at IISc, working in the area of forming methods, where we give the area is essentially giving mathematical guarantees software. Yeah.
Hello everyone, myself Arun Joseph. I'm pursuing PhD in security, system security. So I'm working with Professor Vinod Kanburi. So I'm currently working with some projects related to blockchain, permission blockchain. And in my lab, in broad spectrum, we work in system security aspect.
Hello everyone, my name is Mohit Sharma. I worked as software developer for some 5 years with MediaTek, Amazon, and DirectType. Then I pursued my higher studies again. And currently I'm PhD student working in visualization and graphics lab with Professor Vijan and Rajan. And my area of research is scientific visualization using computational topology, which is a branch of mathematics. And we mainly try to analyze data sets from chemistry, ocean. And along with that, there are works which look for parallel implementation of different structures and algorithms. Thank you.
Hi everyone, my name is Rupasri and I'm a third year PhD student now. I work with Professor Raghavan in Programming Languages Lab. My research primarily focuses on data flow analysis for Akka program. Prior to starting my PhD, I was in the industry for 13 years and my last designation was as a principal architect. Thank you.
Hi everyone, this is Kanmani from Computer Security Lab. So I'm doing my MTech research second year under Professor Vinod Ganapati. So my domain of work is computer security. I'm focusing on device security to identify vulnerabilities.
Good evening, everyone. I am Athar Desai. I am currently my first year PhD student, and I am doing my PhD in systems CSA under Sumit.
Okay, so this session should be an interactive one. This is the time that you ask these people questions, and they will tell you how to get into research, how difficult is research, and so on and so forth. So I mean, you shouldn't be silent. You should be asking questions. So I think I'll give you a chance. So does any one of you have already some question? No, really? Yes.
So the question is for you. So how do you decide to do a PhD after staying in the industry for so long? Both of you have been in the industry for quite a while.
Yeah, that's a common question that I get, and that too after 5 years. So it depends a lot on your career path and priorities, actually. For me, in initial stages of my development career, I was not very sure actually whether it is my interest or I'm just doing it. And after spending few years, and then I realized that I'm not getting that much excitement in just pure development. It's what happens after a time is that you know that these things are solvable. You know that the work which is assigned to you is doable. There is nothing very challenging in that. You get very much familiar with the technologies, tools, languages, and then it's just a matter of manual work of implementing what is supposed to be done. So that was one motivation. And then second motivation was my inclination is more towards teaching, discussion, explanations, rather than just working on a particular project and just sitting at a place. So PhD gave me all of that. It gave me freedom of in terms of choosing the problems or choosing the work that I want to do. Then in terms of very nice intellectual discussions with peers and my advisor. And then of course it's very discussion oriented and you get to ultimately you get to choose a career in academics. So everything was aligned for me. These were few points.
I think my answer would pretty much resemble his. Like, at 13 years, I had seen a lot of the industry. There wasn't a lot of new things to do there. The next role would have been to get into a VP role or a C-suite role or a management, which I didn't want to get into. So the second thing was I wanted to teach. I wanted to get a prep academic. So for me, getting to a PhD was very subjective. And thankfully, everything aligned around that time. I got an admission here and also found an advisor that I wanted to do research with, and the research area particular, because I think you need to stay with it for a long time, like through all the lows and the highs. So I would say a bit of luck and some amount of thinking. So that was the reason I got.
Zainam, I'm a final year undergraduate student. I have a common question to anybody. Means all of you would be doing research in any specific domain, and you would have worked, and there are multiple technologies you would have already seen being deployed or consider. For example, I was for past 1 year I was working more towards blockchain. So when I'm just doing study about that thing, there are many platforms already being Ethereum, Bitcoin, or any other currencies or Hyperledger. But at that time, when I see there are so many flaws and disadvantages, and every time I think that if I could have more time and more knowledge to acquire and build my own platform, something like, did you feel something like every time or any time when you do some research?
Starting. Yeah, so this happens with all the technologies. For example, the blockchain. So the Hyperledger with I am working to it. So it was in a buzz for some time. I think past 2 years ago, it was. I mean, everybody said that it can be used for everything, but then it's proved wrong. Then it can be only used for certain purposes, and it's very. I mean, that's the situation now. Nowadays, I mean, in the top conferences, if you go with a paper with a blockchain, you might get a straight rejection, even if that is good. So that happened with the bus and even ML, NVIDIA with NVIDIA GPU that happened. So it doesn't matter. Like if you are come up with your own idea, and if you have to put a lot of time for it, because these Ethereum, these things are built over the years. Like Bitcoin, thousands of people developed for 12, 13, 14 years, and it's in this stage now. And if you have your own idea, then you have to put equal amount of work to make it work.
So by flaw, do you mean like an engineering flaw or a scientific flaw? I assume engineering at this point, or
design.
What could be a design flaw?
Yeah, means, anytime we think like that, na, means if I had that much knowledge and power, I could have built my own something. But the thing is it possible, or the way we are thinking is always correct or not? That's what I'm asking.
I mean, one thing which comes to my mind is that if you find any flaw or any problem, how do you go about solving it, right? And I mean, I'm sure there are many ways to go about it, either engineering or scientific. But I think one thing for sure, what I like about the PhD process or a research process in general is this, is the flow, is a process. For example, we start off with finding a problem. The problem could be firstly knowing if it's a very good problem, I think we'll solve it before what potentially could contribute to it. That is one aspect. The second is actually going about solving the problem. Maybe you would have a theoretical foundation, or you would show some empirical results, and then you go about writing a paper. Right? Then you write a paper. Now that's another skill in itself. Convincing others how you go about selling it, and finally you would, if your paper gets accepted, you go about marketing it, right? Giving a presentation or something. And this entire process turns you around in a different way, right? And I'll come back to one specific point to answer your flaw, right? So, for example, we won the Ethereum India hackathon last year, right? And there were a lot of problems in the blockchain space. People are coming up with, hey, let's make Shadi.com on blockchain. Like, why? Why would you do that? So the point is the generation of ideas at a level where you're still learning, right? May not be as refined, right? But for example, we came up with an idea where we have this kind of formal, how do you come about finding bugs automatically using all the common methods? Very few people work in my area with common methods, right? So the judges liked it. It's because you are already good at one specific area and you know how to apply that to different areas, right? So the point I'm trying to make is that maybe the right question to ask is, do you want to specifically choose an area, go about finding and solving a niche problem, and in the end, you would end up getting better ideas later on. And for that, you need advisors who could take you to that process. You cannot do that alone, right? And I think that's where the PhD kind of defines you. And of course, each part of this process, for example, if you talk about solving the problem, you're writing code or software engineering is taken care of, right? If you go about towards the end, presenting something, right? You can even teach very well, right? At many layers, by the way. You can teach at undergraduate level, right? You could have, and all the way up to giving a scientific talk, all entail different skills. So at the end of a PhD, you would know exactly where you stand, what you like, and what kind of flaws or problems you want to solve, right? I don't know if I answered the question, but just to give an overview.
Just add few similar points. It's not specifically to your problem. I have no idea about that, but in general, in PhD, the type of problems we encounter, they are unsolved problems, and many times we are actually searching for a problem. That itself is a challenging task. What is there where I can contribute? And from that starting point to the end result, every step is very difficult. But what happens is through these years and throughout this PhD, all these challenges develop our mindset and thought process in a way that we are not very much scared of picking up any new problem, because we know the typically soft skills, how to tackle a new problem, even if I don't have an idea about it. So in a way, the PhD builds you for any type of problem, and it is not specifically a technical problem. Even in general, I feel that has developed me a lot. I look at life in a much different way, which I used to look before. So overall, it builds our thought process. Given any new problem, what are the resources I'm supposed to read? What are the new things I'm supposed to learn? Our learning process becomes very fast. Our searching for resources becomes very fast. We become very smart in filtering out, okay, this is not the section I want to spend effort on. So in general, it builds you in all the segments.
Are any of you planning to, is the primary goal of any of you getting a PhD to enter the industry at a very high level or at a very good job types?
I can actually take that. Actually, people with masters, people with bachelors, and they're becoming VPs faster than others. So PhD is not needed in the industry. Right? That's the reality. In the United States, where I did my master's, I saw people routinely drop out of PhDs because they just want to get into a high-paying job. So although it does allow you, when you're starting off as a PhD, you will probably start off as a software engineer too, when you have a PhD, versus a software engineer one. Right? And after that, it is all your effort. Right? So that was my understanding for this field.
Again, just quick lines on that. Entering into PhD becomes very, very simple and easy for you in case someone wants to pursue a career again in industry after PhD. And that I'm telling you from the very recent experience. I wanted to see how placements are in IISc, and I tried for first week to see what type of things are being asked. And what I felt was where I was 6 years back before joining the PhD, in terms of handling the interviews or in terms of guiding interviews in my way, I'm at a much, much, much better level right now. I was rejecting companies clearly, and I was able to tell them that this is very simple thing you are asking, even if I don't have any idea about this particular field, but I can still give a solution to you. So you are, in terms of intellect level and in terms of handling new problems or new situations, you become so good. And I feel if someone joins industry after PhD, the rate of growth is going to be much faster because you have solved nearly unsolvable problems. You are not going to encounter, you're very rarely going to encounter that in industry.
I think an equivalent question is, I want to join PhD for money. I think joining that is the worst financial decision you can take. Right? So I can be. Again, it depends where you're doing your PhD from. It depends what kind of fellowships you have, right? But I'm sure you all are computer science students. You're better off earning money outside than doing a PhD. So the reasons for doing a PhD should be as strong as what these guys said, right? So
This question I commonly get, the financial thing. Okay, I'll just say one thing on that. People feel that there is more money in industry. I personally feel it's illusion. I can elaborate more on that later. But after so many of my friends are already working in Google, some in US, Zurich, and the input to output ratio, the amount of hours they have to give and the amount of hours I have to give in research versus the return I'm getting is much better in PhD. The return is in many factors. It's not just financial. Ultimately, those finances, I feel, over your long career, you will realize that no, it was not the right way that I chose. But that is still debatable. It can be a long discussion maybe after.
Maybe another workshop.
Yeah.
You feel inner insatisfaction.
Yeah, that's very big, very big. I never felt that during my industry.
Yeah, if you are confused about the long-term commitment in PhD and you want to learn but you are concerned about money also, you can go for MTech research programs where you can try out a research problem. It will be kind of a hybrid between exposing yourself to a job or research work. So in that you can identify if you are really interested in pursuing research. So it will be a much lesser commitment to start with.
One more question. I want. No, I'm not just. I just forget exactly what I wanted to. Let's come back. Okay.
Yeah.
Let's.
Anyone else? I mean, maybe one of you can share your experience. Like
Yeah, I got the question.
Okay.
So the thing is, when you said that you try to find any specific problems that has not been solved, of course you will be working on that. And sometimes how much knowledge and how much base concept you already have, you know the solution that by this way we can solve the problem, but you don't have any way to prove that thing. Then how do you take the steps? Theoretically, you can explain or conceptually you can explain or prove, but not implementation or any other way. Means not.
I think at least in the formal methods and programming analysis space that I am working on, we have specific proofs that we can write. Right? You not only express your ideas in English, you can also express it as pseudocode. And then you can write statements that will say there are certain conditions that will hold before this algorithm runs. And then when the algorithm terminates, it will terminate in this state. Right? And then you can running a single program by program to prove your idea is not a viable solution because they are endless, right? You could write endless number of programs. So you can definitely define a framework, and that's one of the biggest things that I learned, right? At least for me, my learning was in that space. When I came in, I knew how to write code, I knew how to run code, I knew how to deploy code. But what I didn't know was how to argue that my code was correct. Why this was much better than that, right? So one of the first things that the programming analysis and application subject for me, what it taught me was there was a framework. There was something called four triples that you could use to to argue with certain properties of the program, right? And then there were frameworks, right, within which you could fit in your problem statement so that you could argue for it. And then there were testing frameworks that you could deploy to generate a large test space as well, right? So I would say it's a combination of tools, mathematics, and perhaps your argument agility.
Yeah, many times it depends on the type of work you are into, how you are going to prove that what you have presented is correct. The very first thing that should come into mind is the theoretical intuition. You should have an intuition what you are working on, why is it correct? And second thing that should come into mind is, can you mathematically write a rigorous proof that it is correct? Many times it is super challenging. I mean, that's hard part, and that's what we learn throughout PhD, proving that our method is working. And once you are satisfied with your theoretical intuition and if you are able to write that mathematical proof, then we would like to see that in practice, that whatever we thought, is it actually working? Let's say I thought about something that this algorithm is supposed to give me a better performance than some existing algorithm. Theoretically, it was correct, but when I implemented it, there were some technicalities which are making it work worse in, let's say, certain cases or for all the cases. So all that is part of solving any problem throughout PhD, and that is the fun part. If it worked perfectly, okay, that was you would like that. But if it did not work in implementation, then why it failed? Can I improve it in terms of implementation by introducing some, let's say, parallel aspect or some intelligent technique? So all these parts, theoretical intuition, then having a mathematical background, and then having implementation level knowledge, that's what makes you a complete computer scientist, not just a implementer. Yeah.
How mentally you must be prepared before getting into research article? It's a generalized question.
Yeah.
It doesn't matter. It will take a toll at some point. So it is surely, the non-determinism of research is something which nobody prepares you for that. That's the truth, right? You only struggle and somehow figure out how to navigate your way through a research problem. That's the simple answer. I don't know if I have any better answer at this point if I think about it.
Maybe Akal, I don't. So I am a first year PhD student, and I think I'm well qualified to answer this question because I've just done that. So I mean, yes, initially you might feel industry. To be honest, industry you may earn more money than I'm doing when I'm doing my PhD. But the point why I took the PhD was it's not just about solving unsolved problems. It also involves exploring problems that have not been explored before. So it's like there are flaws, but you're solving them in one way, and there is actually another solution which industry may not invest their money because they want profit. So I mean, I would say to a certain extent you'll have to compromise on an earning, but you will miss this excitement if you continue with the job.
So it's very much appropriate question, this how mentally you should prepare. And again, it can be a big session, but see, it's PhD goes from 4 to 6 years and sometimes even goes beyond that. Having that dedication throughout this time, and it's such a long time that even in personal life people face some issues during this time, from family point of view or from some relationship point of view, many things happen. So you have to even deal with that, and while still focusing on PhD. So it's not that you will enjoy throughout, You work on some problems for some 1 year, 1.5 year, and the paper gets rejected. So you should be mentally prepared for those rejections, for those setbacks, for sometimes humiliations. Some faculty may say, "Oh, you know nothing." That also happens. Even if you feel, "Oh, I don't know so much about this field." So everything happens, and again, that also grows you. Like the way you handle failures after overcoming all these issues, that prepares you for life. Failure is a part of it, and you should be ready to it. In PhD, brilliant students can get failures, and someone who was not so brilliant, his PhD may go smooth. And all these things also depend on how good tuning you have with your advisor. So many times I hear that, okay, my advisor is not good or this and that. I feel that every human is different. As long as the student and advisor has a good tuning, the work goes very well. I had zero issues from IISc, from my advisor, and I also took a break from PhD for a year for some personal reasons. I had some issues, and IISc supported that at that time. So I feel that I got all the support and I had absolutely zero issues from PhD. Uh, you have to prepare yourself mentally for sure. It's not an easy task. There are going to be lows and ups. It is going to be there.
Since this is like an important topic, do you have any specific detailed question about the question that you asked?
Yeah, like it's a commitment for many years. You can't jump into any other sector. So that fear, do you have that fear in your research?
So yeah, that fear is there, right? Because
It's a long time commitment.
it's a long. I mean, yeah, it is a long time commitment for sure, right? Or you trick your mind to saying that just 2 more years. But on a serious note, I think the key idea is that, as I mentioned before, research is non-deterministic. Right? You have no idea whether you even get a solution. You're not used to that at this point, right? You look back, you have answers to your questions, and this is not very evident, but and I don't think you'll get the magnitude of what I'm saying right now. But it's actually at some point very difficult to wade through a solution when you're not able to find it. For example, I'll tell you about something about my journey, so I'll be more instantiate. So, 3 years into my problem, I solved it on paper. In the sense, I had the intuition, okay, this will work, but I did not have the necessary background to even formalize it. Or, for example, even if I did, how do I sell it? What are the benchmarks? Who is going to care about it? And that journey itself took me even more years just to find out who cares about this problem. And I had to go around asking people around the world, okay, is this an interesting problem? Why am I wasting my time? Because in the end, I would have wasted my time, right? And that's scary because you have no idea about what's going to happen. But eventually, there are two options: either it works or it doesn't. You will learn both of them for sure, and that's still learning process, right? Once you know, once you have that mindset, I think that's what research teaches you. Or if something works, done, well and good. If something doesn't work, find out why and just move on. And in the end, hopefully, you will have something. Right? That's all you can hope for, and that does prepare you for prepares you mentally for sure, right? I try to make a motivational cringe kind of a quote. If you don't, if your PhD doesn't teach you patience, humility, and diligence, was your PhD even worth it?
So I wanted to add one thing about life and other commitments, right? So when I started PhD, my son was 6 years old. He's in tenth classes with me. He now knows lattices 4 by 9, although he doesn't know the maths behind it. So what I would say is commitments and life will run parallelly. Right? So if you have the interest, you want to do a PhD, I think you should. The skill sets that you will learn is quite nice, apart from writing and presenting skill sets.
Wish better luck for you.
So on the same lines, to choose PhD, what what I feel is few points that one should take care of is one is, and they are not like this is higher priority or that is higher priority. All are at equal level, I feel. One is the area of research. First, go through that's what we do in UG and also in masters. We look at different fields. Okay, what are people doing in algorithms? What are people doing in cryptography? What are people doing in machine learning? What aspect of this particular field do I like? What excites me? That has to be there because you are going to work on that particular field for almost 6 years. If you are not excited about it, you may feel very troubled or you may quit. So field excitement is a must. Then second very important point, the same advisor. Maybe you join some project with that advisor, do some internship in that particular lab, look at the lab environment, look at how that advisor works. Does that suit you well? If everything is comfortable, then you may think of joining that particular lab for PhD. Look at alumni. So if that is one important factor for you, where are alumni placed right now? In which university they got postdoc or they are working right now? Which industry sector they are working right now? If industry is excitement for you. So the points which are important for specifically you that you think if this is not there, I may not be able to go through PhD. Look for those points. Specifically for me, the advisor mattered a lot. I wanted a person with whom I am comfortable working in because it's a 6 years relationship again. Even with your family, in 1 year you have some fights, maybe a month. So many things are going to happen. If the tuning is not good, they will be very frequent, and your productivity will be hampered. So what is very much important for you, whether it's the field, whether it's the alumni, final opportunities after PhD, or whether it's the advisor, look for those aspects.
Yes. Yeah, so you said about the mental makeup, right? So one thing you'll have to remember is your friends and who joined the industry will be earning some X plus X lakhs per annum and all that, and you will be like at what some tens of thousands as scholarship per month. You have to keep that in mind and shouldn't get demotivated by the fact that okay, in the next 6 years I'll be making only so much. But the fact that okay, you have a chance of changing so you're adding to the knowledge of the system as such. And you're improving the knowledge, you're creating the potential of creating the knowledge is vastly more here than compared to the just. So you can come up with a new algorithm. And though a bad example, Larry Page and Sergey Brin were PhD students at Stanford. Then they started Google.
So, in like a master's degree, other than your thesis, it's mostly just coursework. So, how much does a master's degree help you in conducting research? Why can't you just start right off this? How much better?
Yeah, anyway, even if you take more of coursework, research is completely different. Like you have to identify a problem and build basics based on the problem you are working on. So you will need to learn on regular basis to improve your research-based skills.
So the masters and the research is a little different entirely. So while doing the masters, the majority is the coursework. So I mean, I did masters in IISc only, then I continued the PhD. So two journeys are entirely different. But doing the masters, it's like coursework. Like you can't even sleep for 5 hours during especially this period. From second semester, almost January to March, so hard. Like some 16 credits and assignments. Once you submit one assignment, next day is the next deadline. So you move from deadline to deadline. But still, right now, if I look back, that was easy. It's like the problem is defined and the guidelines is given. You just go through that and you think sometimes and you solve it, you code it, you submit it. Done. But now I don't know what to do. Like I have to think and I have to read papers and I have to find different methods so that I can then I have to discuss with my advisor. Then we come up with, okay, we will try this. Then we will try that. After 1 month, okay, it's not working. Okay, throw that away and try new things. Sometimes we try that, and then one another paper comes where the similar approach is there. Then we have to rework and find new things. This happens.
There can be different takes. I feel master's degree can sometimes be redundant and sometimes be important, depending on the candidate. There are candidates after UG who would have moved to PhD from my lab directly. They were very sure, they knew, and they had enough research exposure while staying in the lab. And so for some students who are not very sure sometimes, okay, whether I'm ready for a PhD commitment or not, for them, masters work in two ways. One is if there are some gaps in your UG. I don't know this, I want to improve on this aspect. I didn't know, let's say, I have no machine learning knowledge, or I want to pursue research in this field, but I don't have much strength in terms of mathematics or any aspect. In terms of growing you in that, or second, giving you a feel of research if your master's has a research component attached to it. So in those two aspects, and then you can, if you like the research exposure, you can pursue further PhD. Specifically for me, my master's is from IIIT Hyderabad. It was not research oriented, but since I was good at the basic level things, I wanted to see all the challenging courses. I used to take very difficult courses in every semester. So I wanted to grow in that aspect. Masters helped me there, and while handling those difficulties, that certainly has helped me in conducting research during PhD.
Yeah, I that's more or less what you had said.
So maybe I have one question, or maybe many of them have one question, like how to get into PhD. Since Athar, you just joined or you're the first year, you can comment better.
Um, One way is if you've done a master's here and the project guide approves of you having to go on or continue for a PhD, you can do that. Another way would be to apply through GATE, and there is a third method where I mean, even if you apply through GATE, you have to give an interview. And a third method where if you are from a centrally funded college with a GPA above the cutoff, then you can also directly apply, but you'll have to go through an interview.
Someone can add if he missed some time.
I actually don't remember. I joined 6 years back in terms of admission.
Might change now.
Yeah.
That's why I asked. Yeah, maybe you can also.
It's the same thing what he said. Three ways you can join. One is you should be doing centrally funded degree before this, and everything has a interview. Like you have to pass the interview to come into IISc. So that interview will be like the panel will be faculties who are here. So you can they will ask only like basics of whatever you have done before. Either it might be your masters or bachelor's. So what are basic subjects and a basic syllabus of GATE will be there. So not like advanced things are asked in the interviews. They'll test your basics only. So interview will go on. For me, it went on around like 40 minutes to 1 hour. So they will be very friendly, interactive. They'll give a problem. You have to solve that in front of them, and questions will be there based on your resume.
Okay, I think they will also be. You want to add something? Okay.
Not on that, just one point left untouched, I feel. When we compare with industry or with our friends, what I feel is you should look for what more you will be getting in PhD if you are not earning that money. Whenever my friends visit IISc who are working in organizations right now, they doubt their decision. So you have to grow yourself in those aspects which you feel that you should and you have joined PhD for. They can be non-technical also. So pursue hobbies, which they are very important during research, because otherwise things get very monotonous. grow in those aspects. They'll keep you entertained and they'll keep you moving. Even if you, let's say, face some rejection, you are enjoying some aspect of your life. I'm not saying that just spend all your time in doing that. So there are so many activities which happen in IISc, and students should actually look forward to them also. That they help. They really help.
Now consider I found to be one problem statement, and I'm not saying that I have found the solution, but I think so I can work on that. After doing undergraduate, as you said, we can do the PhD also directly if we find a proper problem statement. So consider I found one problem statement, and now I want to do the PhD at IISc. So how should I reach out and the way to get into PhD?
Yeah, you should start looking for which faculties are working on that particular area. You should start contacting them directly and maybe attend a course that faculty takes and have some discussions on your problem. That will organically take you forward.
I think you can directly email to many of the faculties. I think most of them will reply. I mean, in your case, or in general, if you are doubt about PhD or something, you can still apply for a position or something. Then after say 1 year or 6 months, you get a project assistant position, and you can work with some problem. Either you can propose and discuss to create some problem, or they will suggest some problem. You can work on that and see what the things are doing and whether you are in line with the guides, whatever facility they have. And you can either decide to continue in that lab or you can switch to some other lab and you can go back to. It's kind of experience only. Like payment would be less, but it's a work experience. It's like a proper work experience.
And just add to that, you're right now sitting in IISc and CSA, right? You are at the most advantage. So you could actually email the professor that saying that you're a student here, and you could just ask them if I could just have a meeting for 5 minutes and discuss if you find someone. I think that's the best way.
So what is the process? Consider I reach out to professor, explain my problems with him and how much I have worked till now. All this.
It could be an informal discussion. I think professors here are best to answer that, but I think it should be an informal email in terms of the problem statement that happens.
Yeah, exactly. Formal procedure, I don't know, but UG students have worked as interns in the lab. I think there is some component in the your credits, and while taking their other courses and everything, and the advisor will also making that problem more concrete and maybe solvable or more, which is more of contribution. And while working, you'll get to know where further for PhDs you can apply. So that's what UG students have done. They joined as intern, they worked on a problem for a year. I'm still working with them, and that student has joined University of Utah. So that's how it works. But directly contacting the faculty will help.
Okay. For the interest of the time, we'll stop here. Let's give a brief. So they will also be there during the high tea. So if you have any questions, so please feel free to ask them. So, so maybe, yeah. So we came almost to the end of the session. Not this one. Minimums. No. What are you doing? First start. You don't need this. You don't need this. What? Strange. This sort of things. Okay. Oh, the slide didn't update. Okay. Okay, yeah. Okay, so we are, so yeah. So this is the last presentation you will be looking at. Okay, I promise. No more presentation after that. So yeah, with that, with the last session, we are done with this workshop formally. So I just want to thank all the people behind the workshop. So of course, the attendees, all of you, if you are not here, then there was no workshop. And yes, if attendees are there, there are no speakers, then yes, there was no workshop. So let's thank all the speakers. I want to also thank session chair. So Arka was the session chair on Monday and Deepak was the session chair today. So thanks Deepak, thanks Arka. Of course, I should thank IISc because they allowed me, IISc and CSA, because they allowed us to hold this workshop. And then there was 3 sponsors. Their generous support make this workshop happen. All the good foods you had, all the dinner you had, and the accommodation, all those happened for due to the sponsorship from Kotak IISc AIML Center. CDAC, of course, they spent 2 days with all those boards. They taught you how to use those boards, and AMD. So let's have a big round of applause for the sponsors. Then yes, CSA technical staff, we were doing live streaming for Monday and today. So Akshay and Sanjay helped us a lot for this live streaming. Let's give a big round of applause for them. All CSA staffs, I mean, to do this kind of workshop, we need a huge amount of paper trail, believe me or not. Like, the list of a list containing all of your name are there all over ISC, to the security, to the guest house, all over ISC. So yeah, it needs a huge paper trail. So the CSS staffs were really helpful to manage those paper trails, and paper trails are not so good all the time. So I also want to thank Haridasan and Tares. They were taking all the photos. And he promised me that all the photos will be available by tomorrow. So once he gives me the photos, I will share with all of you. Then yeah, so you're having all the foods and you all told that the food is good. So Rachel's was the caterer, cards and card, printed all the iCard certificate and all those things. And the travels, some of you use the travels, so just was a travels partner. And yes, Office of Communication, they also had a big role to play in this workshop. So we started preparing this workshop all the way from mid-September. So it's a January. So you can see that it took almost 4 months to make this workshop in reality. I want to specially thank Veena, who is speaking from outside. So she really helped a lot in the workshop. I mean, she was one of the organizers. She maintained a lot. I mean, the website you were seeing, it was her doing. So she maintained the workshop. Of course, let's give a big round of applause to them. Then volunteers who are, I think, again, outside this room. I don't know why they're not coming. So Anand, Ajay, Arpit, Avradev, Gulshan, Kirti, Siddhi, Sanjay, Dhaval, Nishit, Milin, Rishikesh. I hope I didn't miss anyone's name. So let's have a big round of applause for them. So one thing is to do this kind of workshop, you need to do a really manage the time. I mean, we are starting at like 9, ending at 5:30. So we couldn't we wouldn't have managed the time if the volunteers wouldn't do their jobs properly. So yes, and so this is a flashback. I think you remember. So if you are not in this photo, that means you didn't attend the CDAC session. And probably you are seeing this slide every day in the morning. So now I think it's time to say goodbye from the workshop. Maybe see you next time. Somebody already say we're not doing it. Okay. So now we'll do a few things. We'll take a group photo here. Okay. And then we'll again go downstairs in the same CSA garden. We'll take another group photo. And then you can have your high tea and then collect your certificates. Sounds good? Okay. So please come front to have a group photo. Whoever is there. Deepak, Viswa, please join.
Thank you, Sumit sir.
Thank you. Just please come forward. If the light becomes low, then there is no point of taking photo in the downspace. So guys, please sit here also. One row can sit. One row can he is the best one. They're standing here. Standing. You need the projector on the back for the backdrop? Okay. I'll switch it off.